Consider the proposition that our reality might be a sophisticated computer simulation created by an advanced civilization, a concept that emerged from philosophical thought experiments but has gained surprising traction among physicists, technologists, and cognitive scientists in recent decades. The argument itself is deceptively simple. If a sufficiently advanced civilization possesses the computational power to create detailed simulations of conscious beings, and if such civilizations might create many such simulations across vast timescales, then statistically speaking, the probability that we exist in the original base reality rather than in one of countless nested simulations becomes vanishingly small. What makes this argument particularly compelling is not merely its mathematical framework, but rather how it reframes our entire relationship with observable reality, suggesting that the laws of physics, the constants of nature, and even the limitations we perceive might all be deliberate constraints imposed by programmers rather than fundamental truths about existence. The psychological mechanism underlying our resistance to this idea operates on multiple levels. We possess an intuitive sense of authenticity and presence that feels too vivid, too continuous, too emotionally resonant to be mere computation, and this visceral conviction functions as a powerful defense against entertaining such possibilities, even hypothetically. Furthermore, the argument creates a strange logical loop, where testing the hypothesis becomes nearly impossible without first accepting the premise that such testing might itself be monitored or constrained by the simulation's architects. Yet we continue to build our civilizations, establish our certainties, and organize our societies as though this question has already been definitively settled in favor of base reality. Consider the peculiar nature of human perception at the finest scales of existence, where reality appears to behave in ways fundamentally inconsistent with continuous, analog experience. When we examine the structure of matter itself, we discover that the universe operates not as a smooth, infinitely divisible continuum, but rather as discrete units of energy and information, quantized into indivisible packets that cannot be subdivided further without ceasing to exist in their original form. This quantization extends throughout nature in ways that should perplex us far more than it does, manifesting in the behavior of light, which exhibits properties of both waves and particles depending on how we observe it, and in the fundamental constants of physics that appear precisely calibrated to allow matter and energy to exist in the first place. At the subatomic level, particles do not occupy definite positions in space until measured, instead existing in probabilistic clouds of potential locations, as though reality requires observation to render itself concrete and specific. The human visual system itself processes the world not as a continuous image, but as discrete frames stitched together by the brain into an apparent seamless experience, with blind spots and temporal gaps that we never consciously perceive because our minds fill in the missing information automatically. We encounter similar pixelation in the structure of time itself, which quantum mechanics suggests may not flow continuously, but rather advances in discrete, unobservable increments, and in our cognitive experience of duration, where subjective moments feel continuous despite being constructed from individual neural firing patterns that occur in measurable intervals. What remains most striking is our collective indifference to these fundamental discontinuities in reality's architecture, our willingness to accept a universe built from discrete, quantum-sized blocks without questioning why existence should operate according to the rules of information processing and rendering rather than flowing like the analog reality we believe ourselves to inhabit. Consider one of the most unsettling experiments in the history of physics, an observation so fundamental that it challenges our understanding of reality itself, and imagine what it might suggest about the nature of the world we inhabit. When scientists fire individual electrons or photons at a barrier containing two slits, something extraordinary occurs that defies conventional logic and material reasoning. If no one observes which slit the particle passes through, it behaves as though it travels through both slits simultaneously, creating an interference pattern on the detector screen behind the barrier, as if the particle exists in multiple states at once. Yet the moment a measurement device is placed to detect exactly which slit the particle uses, the particle instantaneously changes its behavior, abandoning its wave-like properties and passing through only one slit, collapsing into a single defined state. This phenomenon suggests that observation itself fundamentally alters reality, that the act of measurement does not simply reveal pre-existing information, but actively determines what is real. The mechanism underlying this paradox appears to be that particles exist in a superposition of all possible states until observed, at which point reality crystallizes into one definite outcome. Yet this explanation raises deeper questions about what observation truly means and whether consciousness plays a role in collapsing quantum states. We have normalized this behavior by developing complex mathematical frameworks and philosophical interpretations, from Copenhagen interpretation to many worlds theory, each attempting to rationalize how reality can be fundamentally indeterminate until perceived. Yet none fully resolves the core absurdity that existence itself seems to require an observer. If the universe operates on principles where nothing is concrete until measured, where particles can be in multiple places simultaneously until looked upon, then what does this say about the nature of physical reality? In quantum mechanics, one of the most unsettling discoveries emerged from the double-slit experiment, where particles behave differently depending on whether they are being observed or measured, suggesting that the act of observation fundamentally alters reality itself rather than merely revealing it as it already exists. When scientists set up detection equipment to determine which slit an electron passes through, the electron behaves like a particle and produces two distinct bands on a detector screen. Yet when the equipment is removed and no observation occurs, that same electron behaves like a wave and creates an interference pattern with multiple bands, as if it somehow knows it is not being watched and adjusts its behavior accordingly. This phenomenon has been replicated thousands of times across countless laboratories, and it persists at the foundation of quantum theory despite remaining fundamentally inexplicable within our conventional understanding of how reality should operate. The mechanism underlying this paradox appears to involve the notion that measurement inherently requires interaction with a system, and that interaction necessarily disturbs the system being measured. Yet this explanation fails to account for why particles would need to respond to the mere possibility of observation, or why the universe would encode such sensitive, consciousness-dependent behavior into its basic operating principles. We have largely normalized this bizarre reality by compartmentalizing quantum mechanics into its own theoretical domain, treating it as a set of mathematical rules that work reliably for predictions without requiring us to genuinely confront what it means that observation creates reality rather than discovers it. When two particles become entangled at the quantum level, they form a connection so profound that measuring one particle instantaneously affects the other, regardless of the distance separating them, even if they exist on opposite sides of the universe with no possible communication between them. This phenomenon has been experimentally verified countless times in laboratories around the world, yet it violates one of our most fundamental assumptions about how reality should function. Einstein himself called this spooky action at a distance because he found it deeply troubling, and yet modern physics has confirmed that this is not merely possible but inevitable within quantum mechanics. The particles do not send signals to each other, no information travels between them, and yet the correlation is absolute and instantaneous, suggesting that our understanding of space, time, and causality might be fundamentally incomplete or perhaps deliberately constrained. If we consider that a simulation would require optimization to function efficiently, entanglement becomes remarkably elegant as a computational shortcut. Rather than calculating the properties of two particles independently across vast distances, a simulator could simply link them as variables in the same system, updating both simultaneously with no data transmission required. The fact that entanglement works perfectly, that it persists despite decades of attempts to find hidden variables or classical explanations, and that it operates at scales from photons to increasingly larger objects suggests a system designed with mathematical elegance in mind. We have normalized this impossibility by accepting it as simply how quantum mechanics works, by wrapping it in mathematical formalism and moving forward with our research, yet we rarely pause to acknowledge how utterly bizarre it is that reality permits such non-local connections. The Mandela Effect represents one of the most unsettling collective memory phenomena in modern times, named after the widespread false recollection that Nelson Mandela died in prison during the 1980s, when in fact he was released and lived until 2013. What makes this phenomenon particularly striking is that thousands of people across the globe share identical false memories of events that never occurred, remembering details with such conviction that they become shocked upon discovering their recollection contradicts documented reality. Consider the Berenstain Bears, which millions recall as Berenstain Bears despite the spelling always having been Berenstain since the series' inception in 1960. Or the iconic Monopoly mascot Mr. Monopoly, whom countless people distinctly remember wearing a monocle, though historical records and original game materials show he never did. Then there is the Shazam movie of the 1990s, which legions of people vividly recall watching as children, remembering specific plot details and scenes, despite the film never existing in any form whatsoever. The mechanism behind this phenomenon appears rooted in how human memory functions, operating not as a perfect recording device, but as a reconstructive process that fills gaps with logical assumptions and patterns. Our brains unconsciously correct what seems wrong, completing incomplete information based on expectations and linguistic patterns, so that Berenstain becomes Berenstein because it follows familiar naming conventions, and a monocle seems perfectly aligned with the wealthy caricature of Monopoly. These false memories spread through social reinforcement, where conversations with others who share the same error create a feedback loop that strengthens the false recollection further. What proves genuinely perplexing is how these collective delusions persist even after being corrected, how people encounter photographic evidence contradicting their memories yet remain partially unconvinced, as though some deeper layer of their consciousness insists on the false version. In 1954, physicist Enrico Fermi posed a question that has haunted the scientific imagination ever since. If the universe contains billions of galaxies, each with billions of stars, and the statistical probability of life emerging is reasonably high, then where is everybody? This paradox sits at the intersection of cosmology and astrobiology, presenting us with a universe that appears mathematically teeming with intelligent civilizations, yet remains eerily, impossibly silent. We listen with our most sensitive instruments, we scan the electromagnetic spectrum for signals, and we find nothing but cosmic static. The sheer scale of the universe suggests that extraterrestrial life should be common, perhaps even mundane, yet our telescopes and receivers encounter only deafening silence. This contradiction generates a peculiar cognitive dissonance, because our rational calculations insist that civilization must be out there somewhere, yet our empirical observations provide not a single confirmed detection. The psychological mechanism underlying our acceptance of this paradox involves what might be called existential compartmentalization. We simultaneously hold two contradictory beliefs without fully acknowledging their incompatibility. We accept the Drake equation and the vast statistics suggesting countless worlds, while also accepting that we have never found evidence of any other civilization despite decades of searching. We rationalize this silence through filter theories, suggesting that civilizations invariably destroy themselves, or that life requires such specific conditions that it becomes vanishingly rare, or that intelligent species inevitably develop weapons that end their existence before they can reach the stars. Yet these explanations feel increasingly like comfortable stories we tell ourselves, narratives designed to resolve the discomfort of living in what should be a crowded cosmos but feels like isolation. Consider the mathematical precision required for existence itself, a phenomenon so extraordinary that physicists have spent decades struggling to explain why our universe appears calibrated with almost impossible exactness to permit life. The constants of nature, the strength of gravity, the charge of the electron, the expansion rate of space itself, exist within such narrow ranges that even infinitesimal variations would render stars impossible, atoms unstable, and chemistry itself a meaningless concept. If gravity were slightly stronger, massive stars would burn out in mere millions of years, far too quickly for life to evolve. If slightly weaker, stars would never form at all, and the universe would remain an eternal expanse of diffuse hydrogen. The fine structure constant, which determines how atoms bind together, sits at a value so precise that if it varied by more than 4% in either direction, carbon-based life would become impossible, and with it, every living thing we know. These are not rough approximations or statistical probabilities. These are specifications so exact that they seem almost deliberately engineered, as though someone adjusted dials with meticulous care before pressing start. Our psychological response to this reality has been to rationalize it through the multiverse hypothesis, suggesting that countless universes exist with different constants, and we simply happen to inhabit the one rare universe where the numbers work out, much like finding ourselves on the only planet in existence that permits observers to exist. This explanation, while logically sound in theory, requires believing in infinite realities that can never be observed, tested, or verified, asking us to embrace unfalsifiable metaphysics rather than acknowledge the strangeness of our situation. We have normalized this cosmic conspiracy of numbers so thoroughly that we discuss it in academic settings as though it presents no philosophical difficulty. Compartmentalizing the question into probability puzzles and selection bias rather than confronting the deeper wonder of why mathematical reality itself permits conscious observers at all. In 1935, physicist Erwin Schrödinger proposed a thought experiment that would become one of the most troubling illustrations of quantum mechanics' fundamental strangeness, and the paradox operates like this. Imagine a sealed box containing a living cat, a radioactive atom, a radiation detector, and a vial of poison gas, where the atom has a 50% chance of decaying within 1 hour, and if it decays, the detector triggers, releasing the poison and killing the cat. But if it does not decay, the cat remains alive. And here is where the quantum weirdness emerges, because according to the mathematics of quantum mechanics, before we open the box to observe what has happened, the radioactive atom exists in what physicists call a sewer position, meaning it is simultaneously both decayed and undecayed, which would logically mean the cat is simultaneously both alive and dead, existing in both states at once, until the moment of observation collapses this superposition into one definite reality. The mechanism that creates this impossible situation stems from the measurement problem in quantum mechanics, which suggests that subatomic particles do not possess definite properties until they are observed, and that the act of observation itself fundamentally changes the system being measured, forcing reality to choose a definite state. Yet Schrödinger created his cat specifically to show how absurd this interpretation becomes when applied to everyday macroscopic objects like living creatures. Because no reasonable person would argue that a cat is actually both alive and dead simultaneously in any meaningful sense. Consider the moment when you walk into a room, a cafe, or a street corner, and something about the experience strikes you as profoundly familiar, as though you have lived through this exact moment before, down to the smallest details of light and shadow, conversation and gesture, yet you know with absolute certainty that this is your first time in this location. The sensation is vivid and undeniable, flooding your consciousness with an inexplicable sense of recognition that feels almost like a glitch in your perception of time itself. You might remember the specific weather, the arrangement of objects, even the tone of a stranger's voice, all of it converging in your mind as something you have already experienced. The French term déjà vu, meaning already seen, captures this phenomenon that occurs in roughly 60 to 70% of the population at least once in their lives, and in some individuals, it becomes a recurring experience that defies easy explanation. Psychologists and neuroscientists have proposed various mechanisms to account for this sensation, suggesting that it may result from a temporary mismatch between memory encoding and retrieval systems in the brain, or perhaps a brief delay in the processing of sensory information that creates an illusion of false recognition. Others propose that certain environmental patterns trigger memories of superficially similar experiences, which our minds then conflate into a feeling of absolute familiarity. Yet despite these frameworks, the phenomenon persists as something we have normalized rather than truly understood, a quirk of consciousness that we acknowledge, discuss briefly, and then move forward from without demanding deeper answers. We live in a world where millions experience this inexplicable sensation daily, where the boundary between genuine memory and illusory recognition becomes momentarily blurred, and we have simply accepted that our brains occasionally misfire in ways that create the sensation of reliving moments we have never actually lived through. Consider the peculiar nature of speed limits on our roads and highways, those numerical markers that dictate how fast we are permitted to travel in our vehicles, boundaries that exist as painted signs and legal codes, yet somehow govern millions of individual decisions every single day. We accept without question that there is a maximum velocity beyond which we transform from law-abiding citizens into criminals, that crossing an invisible threshold of kilometers or miles per hour represents a violation worthy of fines, points on licenses, and even imprisonment in extreme cases. Yet when we examine this system more closely, we discover something fundamentally illogical at its core. The speed limit is not actually a limit at all, but rather a statistical guess, a number chosen by bureaucrats based on road conditions, traffic patterns, and accident data that was collected months or years before the current moment. The posted limit on a sunny afternoon remains identical to the limit during a torrential downpour, despite the fact that the actual safe speed varies dramatically depending on weather, time of day, traffic density, vehicle condition, and driver capability. We have created an elaborate enforcement mechanism, complete with radar guns, hidden vehicles, and surveillance technology, to ensure compliance with a number that bears no relationship to real-time conditions or the actual physics of safe travel. What makes this paradox even more striking is that we have collectively agreed to this fiction so completely that we experience genuine moral condemnation toward those who exceed the posted limit, even when doing so is objectively safer than adhering to it, as when driving faster than the posted speed on an empty highway during clear conditions with excellent visibility. Consider the foundational nature of matter itself, where light and subatomic particles exist in a state of fundamental contradiction that defies classical logic and challenges the very structure of reality as we understand it. When observed through certain experimental apparatus, an electron behaves as a discrete particle with definable position and momentum, existing at a specific location in space and time. Yet when that same electron is not directly observed, it behaves as a wave spreading across space simultaneously and interfering with itself in patterns that can only be explained through wave mechanics and probability distributions. The moment a measurement is attempted, the wave function collapses into particle behavior, as though reality itself reshapes based on whether we are watching. This is not merely a limitation of our instruments or our knowledge, but appears to be a fundamental feature of existence at the quantum scale. The psychological mechanism that allows us to accept this paradox operates through compartmentalization and mathematical abstraction. We have developed sophisticated mathematical frameworks called quantum mechanics that perfectly predict the outcomes of these experiments with extraordinary precision, and this predictive success has allowed us to suspend the requirement for intuitive understanding. Our minds accept the equations as sufficient explanation, even though the equations themselves do not resolve the underlying contradiction, but merely describe it with mathematical elegance. We have normalized the existence of something that cannot simultaneously be both a particle and a wave by deciding that the question of what it truly is represents a category error, a misunderstanding of the nature of quantum reality itself. What persists is our acceptance that the universe operates according to rules fundamentally alien to human perception and logic, yet we rarely question whether such an incoherent foundation suggests something deeper about the nature of reality's construction. At the quantum level, physicists discovered something that should have remained confined to abstract mathematics, yet it appears to govern the very fabric of our reality. The more precisely you measure one property of a particle, the less you can know about another complementary property, as if the universe itself is designed to withhold complete information from any observer. When you attempt to determine the exact position of an electron, its momentum becomes fundamentally unknowable, and when you reverse this measurement, the position dissolves into uncertainty, creating a perfect cosmic trade-off that seems almost programmed into existence. This principle, formulated by Werner Heisenberg in 1927, should theoretically only apply to subatomic particles in laboratories, yet the pattern extends into every domain of human experience in ways that suggest a deliberate architectural choice rather than coincidence. Consider how the more you focus intensely on achieving one life goal, the less aware you become of opportunities in other directions, or how the more transparent and observable a system becomes, the more it begins to change its behavior, almost as though consciousness itself is being monitored and constrained. In romantic relationships, the moment you demand absolute certainty about someone's feelings, their actual emotions become impossible to determine accurately. And conversely, the more you allow mystery and space, the clearer the authentic connection becomes, suggesting that observation itself is the corrupting agent. The principle persists despite having no logical necessity in the classical world, yet we experience it constantly in decision-making, where perfect information about all consequences of a choice remains forever inaccessible, forcing every major decision into a state of calculated risk rather than certainty. At the foundation of physical reality, particles exist in a state called superposition, meaning they simultaneously occupy multiple positions, possess multiple properties, and exist in multiple states at once until the moment they are observed or measured. An electron can be here and there and everywhere in between all at the same time, existing as a kind of ghostly probability cloud rather than a definite object. And this is not merely a limitation of our measuring instruments or our knowledge, but rather appears to be the actual nature of reality itself at the quantum scale. The particle only chooses a single definite state the instant we attempt to observe it, collapsing from infinite possibilities into one concrete reality, as if the universe operates according to a principle that existence itself requires an observer to become real. This phenomenon, verified countless times through rigorous experimentation and embedded into the mathematical framework of quantum mechanics, suggests something deeply paradoxical about the nature of reality. Nothing has a definite state until consciousness or measurement interacts with it. The mechanism underlying this apparent impossibility involves what physicists call the wave function, a mathematical description that captures all possible states simultaneously, yet when reality is actually measured, only one state manifests while all others vanish instantaneously. Perhaps most strangely, the act of observation itself determines the outcome, meaning the universe appears to respond directly to consciousness in ways that defy classical logic and suggest an almost responsive, reactive quality to physical reality itself. We have integrated this profound paradox so deeply into scientific orthodoxy that it scarcely provokes wonder anymore, yet the core assertion remains extraordinary. The universe does not exist in definite form independent of observation. Particles genuinely exist in all states simultaneously, and measurement fundamentally alters what is real. Consider the philosophical thought experiment that has haunted epistemology for decades. Imagine your brain suspended in a vat of nutrient-rich fluid, connected to a sophisticated computer that simulates all sensory experiences with perfect fidelity, sending electrical signals that your brain interprets as sight, sound, touch, taste, and smell, creating an entirely convincing reality that feels indistinguishable from genuine experience. This brain would have no way to detect the deception because every thought it generates, every memory it forms, every sense of certainty it experiences would be artificially constructed by the simulation feeding it information. The profound, unsettling aspect of this scenario is not merely its theoretical possibility, but rather how it exposes a fundamental vulnerability in human consciousness. We have no direct access to objective reality whatsoever, only to the interpretations our brains create from sensory data. Our entire experience of existence is mediated through electrochemical processes in our skulls, meaning that subjectively, a perfectly simulated reality would be indistinguishable from an authentic one. This raises an insurmountable epistemological problem because it demonstrates that certainty itself becomes impossible. We cannot prove we are not brains in vats because any proof we attempt to construct originates from the potentially simulated perceptions we are trying to verify. The mechanism underlying this paradox operates on a fundamental truth about consciousness. We experience reality only through neural interpretation, never through unmediated access to external phenomena. Every color you perceive, every sound you hear, every physical sensation you feel is actually a constructed representation within your brain's processing centers, not a direct encounter with the thing itself. Consider the fundamental nature of black holes and what physicists discovered when they began studying them in earnest during the late 20th century. Scientists found that the information content of a black hole, the total amount of data that can be encoded within it, is not proportional to its volume as one might logically expect, but rather to the surface area of its event horizon. This discovery led theoretical physicists like Juan Maldacena and others to propose what became known as the Holographic Principle, the radical notion that all the information contained within a three-dimensional region of space can be fully described by information encoded on its two-dimensional boundary. Much as a hologram contains all the necessary data to project a complete three-dimensional image from a flat surface. Applied to our universe itself, this suggests that everything we experience, all the depth and complexity and apparent three-dimensionality of reality, might be nothing more than a projection arising from information encoded on a distant cosmic boundary, a notion that seems impossible on its surface and yet has become increasingly central to theoretical physics and the study of quantum mechanics. The psychological mechanism that allows us to accept this contradiction lies in our tendency to separate abstract mathematical principles from experiential reality, treating theoretical frameworks as separate from the physical world they describe. Yet the principle persists because the mathematics works with undeniable consistency, and because the observations in quantum mechanics and gravitational physics seem to demand some explanation that bridges the gap between them. We have normalized this paradox by treating it as a beautiful mathematical curiosity rather than facing the disturbing implication directly, that the dimension we inhabit and experience as real might be fundamentally illusory, an elaborate projection cast from a realm we cannot access, much as characters in a two-dimensional film might never comprehend the projector creating their world. Consider the ancient Greek philosopher Zeno of Elea, who proposed a thought experiment that has haunted mathematics and logic for over 2,000 years. If you wish to travel from one point to another, you must first cover half the distance, then half of the remaining distance, then half of that distance, and so on infinitely, dividing the space into an endless series of smaller intervals that must theoretically be traversed one after another before you can ever complete your journey, which means that motion itself becomes logically impossible because you would need infinite time to complete an infinite number of steps, yet somehow we all move. We all travel, we all reach our destinations every single day without experiencing this infinite regression. The paradox exists because there appears to be a genuine logical contradiction between what mathematics tells us should be theoretically required for motion to occur and what empirically happens in reality, where objects move freely and arrive at their intended locations without becoming paralyzed by infinite subdivision. The mechanism behind this paradox lies in our intuitive understanding of infinity and divisibility, concepts that seem perfectly reasonable when examined through pure logic, but which collapse under scrutiny because infinite series can still sum to finite values, something our ancestors could not properly calculate and therefore could not refute Zeno's claims with mathematical precision. Consider a statement so deceptively simple that it breaks the entire foundation of logic itself. This statement is false. When you examine it, you find yourself caught in an impossible loop that no amount of reasoning can resolve, for if the statement is true, then it must be false, and if it is false, then it must be true, creating an infinite regression that collapses the very concept of truth and falsehood upon which all rational discourse depends. This ancient paradox, attributed to the Greek philosopher Eubulides of Miletus, has haunted philosophy and mathematics for thousands of years, yet we continue to build our entire civilization on the assumption that all statements can be classified as either true or false, despite this glaring counterexample that proves otherwise. The mechanism behind this paradox reveals something profoundly unsettling about the nature of language and logic itself. Self-reference becomes pathological when combined with negation, creating a system that cannot bootstrap itself into consistency without introducing external limitations or hierarchical layers of truth that themselves become questionable. What makes this paradox so deeply troubling is that it is not merely a quirk of language or an abstract mathematical curiosity, but rather a fundamental flaw in the very framework we use to understand reality, communicate with one another, and build scientific theories that purport to describe how the universe operates. We encounter versions of this paradox constantly in everyday life, whenever we engage with irony, sarcasm, or social contradiction. Yet we have somehow normalized living within these logical impossibilities by simply accepting ambiguity and context dependency as features rather than bugs of human communication. Imagine prisoners chained in a cave since childhood, facing a wall where shadows dance before them, cast by a fire burning behind them and objects carried between the fire and the wall. And these prisoners, knowing nothing else, believe the shadows are reality itself, the only reality that exists or has ever existed. One day a prisoner escapes, turns around, sees the fire creating the illusions, walks toward the light, and eventually exits the cave into the real world where sunlight reveals objects in 3 dimensions with color and depth and texture. Yet when this freed prisoner returns to tell the others what he has discovered, the remaining prisoners mock him, ridicule his dilated pupils that can no longer see the shadows clearly, and threaten violence against anyone who attempts their liberation. This ancient allegory describes our modern condition with unsettling precision, for we too inhabit a carefully constructed environment of projected information, curated narratives, and algorithmically selected content that our minds accept as comprehensive reality. We scroll through two-dimensional screens displaying shadows of human experience, edited highlight reels, manufactured controversies, algorithmic reinforcements of our existing beliefs. While the mechanisms creating these projections remain hidden behind technological firewalls we rarely examine. Our education systems, media institutions, and digital ecosystems function as the fire and wall, continuously projecting a specific version of reality onto the screens of our perception, and we have grown so accustomed to these shadows that we mistake them for the full spectrum of what is knowable and true. In 1931, mathematician Kurt Gödel proved something that should have shattered our understanding of reality itself. Any logical system complex enough to describe arithmetic contains statements that are true but cannot be proven within that system, and no system can prove its own consistency. This theorem suggests that the universe operates under rules that transcend complete logical description, meaning there will always be gaps, always be truths beyond reach, always be questions that cannot be answered from within the framework we inhabit. If we exist within a simulation, the code that governs it would be subject to the same mathematical constraints, implying that the simulation's creators could not have fully verified their own creation, could not have mathematically proven that the system they built is internally consistent and free from logical contradictions. The psychological mechanism at work is that we've constructed an entire civilization on the assumption that logic and mathematics are universal truths capable of eventually explaining everything. Yet Gödel's theorem proves this assumption fundamentally false, creating a cognitive dissonance we've learned to ignore. We built science, philosophy, and artificial intelligence on the promise that if we just gather enough data and apply enough reason, we can solve any problem and understand any mystery. But mathematics itself reveals an eternal incompleteness that no amount of observation or computation can overcome. The peculiar aspect of how we've normalized this is that Gödel's theorem is taught in universities as an interesting mathematical curiosity rather than the profound philosophical crisis it represents. A stunning revelation about the inherent limits of any closed system treated as merely academic trivia rather than fundamental evidence of something incomplete about our reality itself. Consider the famous paradox that has perplexed philosophers for millennia, the Ship of Theseus, which begins with a vessel that sails the seas and over time requires maintenance and repair as its wooden planks weather and decay from exposure to salt water and time. One by one, each plank is carefully removed and replaced with new timber until eventually, after many years of continuous voyages and restoration, not a single original piece of the ship remains. The question then emerges, is this still the same ship? At what precise moment did it cease to be the original and become something entirely new? Furthermore, imagine that a craftsman collected all the old, discarded planks from the original vessel and painstakingly reconstructed them into a complete ship using the original materials in their original arrangement. Now two ships exist, one that has been continuously maintained and sailed, and one made from the original components. Which one is truly the Ship of Theseus? Our daily lives contain countless examples of this identical paradox operating beneath the surface of our consciousness. Your body replaces the majority of its cells over the course of 7 to 10 years, meaning that the physical matter comprising you now is almost entirely different from the physical matter that made up your body a decade ago, yet you remain convinced of your continuous, unchanging identity. Your personality shifts, your memories fade and transform, your values evolve, and your relationships transform, yet society insists on treating you as the same legal and moral entity throughout your entire existence. Corporations maintain their identities despite complete turnover of employees, founders, leadership, and even business models and locations. Our nations remain conceptually unified while their citizens, governments, laws, and territories undergo radical transformation across generations. We have normalized this paradox so thoroughly that it almost never registers as paradoxical at all. We simply accept that identity persists through complete material and structural replacement without ever demanding a coherent explanation for how this is possible. Imagine stepping into a time machine and traveling backward through the decades, centuries, or millennia to a moment before your own birth, and then you commit an act that prevents your grandfather from ever meeting your grandmother, or perhaps you prevent your grandfather from ever being born at all, which would mean your parent could never exist, and therefore you could never exist. And yet here you stand in this paradox fully formed and conscious and capable of making these choices. The grandfather paradox represents one of the most fundamental logical impossibilities that should theoretically be impossible to resolve, and yet it persists as a thought experiment that everyone understands intuitively despite its unsolvable nature. The mechanism behind this paradox is deceptively simple. Causality appears to flow in only one direction through time in our observable universe, and linear causality demands that effects cannot precede causes, that children cannot be born before parents, that consequences must follow from prior events in an unbroken chain of dependency. But the grandfather paradox creates a logical knot where the effect and cause become inverted and impossible, where your very existence becomes contingent upon an action you take that would retroactively erase your existence before you could take that action. What makes this paradox particularly relevant to simulation theory is that it suggests our universe operates with built-in safeguards or restrictions, similar to how a programmer might create immutable laws or prevent certain operations that would crash the system or create infinite loops. In simulated reality, such paradoxes might not be bugs, but rather features, constraints deliberately encoded to maintain computational stability and logical coherence, preventing users from accessing time manipulation functions that would destabilize the entire environment. In quantum mechanics, there exists an experiment so deeply paradoxical that it seems to violate the fundamental rules of causality itself, and it is called the delayed choice quantum eraser. The basic setup involves a photon being sent through a double-slit apparatus, where it should theoretically pass through both slits simultaneously as a wave and create an interference pattern on a detector screen behind it. Yet when we place a measuring device to determine which slit the photon actually passes through, the interference pattern mysteriously vanishes, and we see only two distinct bands, as though the photon had suddenly decided to behave as a particle instead. The profound strangeness emerges in the delayed choice version, where the decision to measure or erase that measurement information is made after the photon has already passed through the slits. Yet somehow the photon's behavior retroactively adjusts to match our later choice, as if the future is causally influencing the past in a way that should be impossible according to everything we understand about time and causality. The mechanism operates through quantum superposition and the nature of observation itself, where the existence of which path information in the system collapses the wave function into a definite state. But when that information is later erased through a quantum operation, the wave function somehow reconstructs itself retroactively, and the interference pattern reappears, suggesting that reality itself is not determined until we make a measurement. And that time operates in ways fundamentally different from our classical intuition. In the vast expanse of an eternally expanding universe governed by the second law of thermodynamics, a peculiar mathematical possibility emerges that challenges our fundamental assumptions about consciousness and reality itself. According to quantum mechanics and statistical mechanics, if the universe has infinite time to exist, random molecular fluctuations could theoretically assemble themselves into conscious minds, complete with false memories of having lived entire lives, existing for mere moments before dissolving back into entropy. These hypothetical entities are called Boltzmann Brains, named after the physicist Ludwig Boltzmann, who first pondered this disturbing implication of infinite time and random chance. The mechanism behind this concept relies on the understanding that any arrangement of matter, no matter how improbable, becomes statistically inevitable given enough time, and consciousness itself requires only the right organization of particles to generate subjective experience and thought. What makes this notion so philosophically troubling is that if Boltzmann brains can form spontaneously from quantum fluctuations in the future universe, then statistically speaking, isolated conscious minds experiencing delusional memories would be vastly more common than beings like us with coherent life histories emerging from stable, organized civilizations. The implication becomes unavoidable. If this principle holds true, the probability that you, right now, are actually a Boltzmann brain hallucinating an entire consistent reality, rather than a genuine conscious being living in an actual universe, becomes disturbingly difficult to dismiss through reason alone. Yet we persist in our conviction that we are real, that our memories are accurate, and that an external world exists independent of our perception, despite having no empirical method to definitively rule out the Boltzmann brain hypothesis, suggesting either that something in our universe prevents this phenomenon or that we have fundamentally misunderstood the nature of probability, consciousness, and existence itself. Imagine a musician traveling backward in time with a completed symphony, handing it to their younger self decades before it was written, thereby creating a causal loop where the music exists but was never actually composed by anyone. This is the Bootstrap Paradox, and it represents one of the most perplexing logical impossibilities in theoretical physics and temporal mechanics, yet it also exists in a far more subtle form throughout our everyday reality. Information and knowledge appear to originate from nowhere, emerging fully formed without any identifiable source or creator, circulating endlessly through human culture and consciousness in ways that defy rational explanation of their initial genesis. Consider how ideas spread through societies, how ancient wisdom appears in cultures separated by vast distances with no possible means of contact, or how scientific principles seem to exist in the universe independent of anyone discovering them, suggesting they were always present waiting to be uncovered rather than invented. The psychological mechanism sustaining this paradox operates through our tacit acceptance that some things simply exist without requiring explanation of their origin, a profound cognitive bypass that allows us to function despite encountering information with no discernible source. We encounter memes, cultural artifacts, and conceptual frameworks that persist across generations with no clear point of creation, as if they had always existed in some platonic realm awaiting human discovery rather than human invention. The paradox persists because we have normalized our ignorance of true origins, accepting that Newton's laws governed the universe before Newton existed, that mathematical truths transcend human existence, and that certain ideas achieve such ubiquity that their original source becomes permanently obscured beneath layers of transmission and replication. Consider the fundamental structure of mathematics and logic itself, which underpins everything we believe we know about reality, and you will encounter a problem so elegantly self-defeating that it threatens the very foundations upon which rational thought is built. In the late 19th century, the mathematician Bertrand Russell discovered a contradiction lurking within set theory, the mathematical framework designed to organize all possible collections of objects into orderly categories. The paradox presents itself through a deceptively simple question. If we create a set of all sets that do not contain themselves as members, does this set contain itself or not? If it does contain itself, then by definition it should not, because it is defined as containing only sets that do not contain themselves. Yet if it does not contain itself, then by the same logic it must contain itself, because it meets the criteria for inclusion. We find ourselves locked in an impossible loop, a logical Ouroboros where the answer contradicts itself no matter which direction we approach the problem from. This is not merely a theoretical curiosity confined to academic discourse, but rather a profound revelation about the nature of self-reference and categorization itself. The mechanism underlying this paradox reveals that language and formal systems possess inherent limitations when attempting to describe themselves or their own rules. When systems become sufficiently complex and self-referential, they inevitably generate statements that cannot be assigned a consistent truth value within their own framework. Despite the discovery of this fundamental flaw in mathematical logic over a century ago, we have not abandoned mathematics or logic, nor have we solved the paradox in any way that completely eliminates its troubling implications. Instead, we have normalized its existence by establishing careful restrictions and boundaries around what kinds of sets we allow, working around the problem rather than through it, much like building architecture around a fault line in the earth rather than repairing the fault itself. Consider the peculiar logical breakdown known as the twin paradox, a thought experiment embedded within Einstein's theory of relativity that reveals something unsettling about the nature of time and motion within our supposedly deterministic universe. The paradox presents two identical twins, one of whom remains on Earth while the other embarks on a space journey traveling at speeds approaching the speed of light. And according to the mathematics of special relativity, time dilation dictates that the traveling twin should age more slowly than their stationary sibling, meaning that upon returning to Earth, the traveling twin would be measurably younger than their Earth-bound counterpart. This result has been experimentally verified through atomic clocks transported on aircraft and satellites. Yet the paradox emerges not from the physics itself, but from the fundamental violation of our intuitive understanding of reality, because the very concept of relative time seems to contradict the notion that time is a universal constant, flowing uniformly for all observers regardless of their motion through space. The mechanism underlying this persistence of the paradox stems from humanity's deep psychological investment in classical Newtonian intuitions about the nature of time and simultaneity, concepts so deeply embedded in human consciousness during childhood that they resist replacement even when presented with empirical evidence and mathematical proof. We have normalized this paradox by compartmentalizing it into the domain of theoretical physics, treating it as a curiosity that applies only to extreme velocities and exotic conditions, rather than confronting the deeper implication that our subjective experience of time may be fundamentally illusory, or at least far more malleable than conscious reality appears to permit. In 1861, Scottish physicist James Clerk Maxwell proposed a thought experiment that would haunt physics for generations. Imagine a tiny creature, a demon, standing at a microscopic door between two chambers of gas at equal temperature. This demon could observe individual molecules approaching the door and selectively allow fast-moving molecules into one chamber while blocking slow-moving molecules from entering the other. Over time, one chamber would grow hot while the other grew cold, seemingly creating energy from nothing and violating the second law of thermodynamics, which states that entropy always increases. The demon represents a fundamental paradox in how we understand the universe, a logical impossibility that should not exist, yet the thought experiment persists because it reveals something unsettling about the nature of observation, information, and control itself. The psychological mechanism at work here is our deep human desire to find loopholes in absolute laws, to discover that with sufficient knowledge and precise action, we could reverse entropy and undo the universe's inevitable decay toward disorder. We want to believe that consciousness and selective attention can reshape reality at its foundations, that by carefully choosing what we observe and manipulate, we could engineer systems that defy the basic rules governing existence. The demon's appeal lies in its seductive promise. If only we were intelligent enough, if only we possessed perfect information about the microscopic world, if only we could act with absolute precision and zero cost, then we could cheat thermodynamics itself. Yet for over a century and a half, physicists have demonstrated that the demon cannot actually work, that the very act of acquiring information about molecular states, the energy required to operate the door, and the entropy generated by the demon's measurement process all work together to ensure the second law remains unviolated. Consider the extraordinary fact that the universe appears precisely calibrated for human existence, a phenomenon so improbable that physicists have struggled for decades to explain it without invoking divine intervention or design. The fundamental constants of physics, the strength of gravity, the electromagnetic force, the mass of electrons, the expansion rate of the universe itself, all fall within vanishingly narrow ranges that permit stars to form, planets to coalesce, and ultimately, conscious beings to emerge and contemplate their own existence. If any of these constants deviated by even a fraction of a percent, matter would either collapse into black holes or scatter into cold emptiness, rendering chemistry impossible and life inconceivable. Yet here we stand, asking why the cosmos appears engineered specifically for us. The Anthropic Principle suggests a deceptively simple answer. We observe a universe fine-tuned for life because we could not possibly observe any other kind. We are necessarily prisoners of a universe capable of producing observers, making our existence the only universe we could ever witness. This explanation, while logically coherent, masks a profound discomfort that persists at the deepest levels of scientific inquiry. We have normalized an answer that essentially transforms an extraordinary cosmic coincidence into a tautology, a logical certainty that feels unsatisfying precisely because it removes the mystery rather than resolving it. The universe did not arrange itself for us. Rather, the argument suggests we could only ever find ourselves in a universe already arranged this way, yet this reasoning does nothing to address the haunting question of why such a universe exists at all. We continue our research with this principle as a foundation, accepting that some questions may be unanswerable within the framework of observable reality, a limitation that quietly suggests the boundaries of what science can explain about our existence. Consider the uncomfortable intersection between quantum mechanics and consciousness, a theoretical framework that suggests that from your subjective point of view, you may never actually experience death. The mechanism works like this. According to certain interpretations of quantum theory, every possible outcome of an event occurs across different branches of reality, and your consciousness can only ever experience the branches in which you continue to exist. This means that no matter how statistically improbable your survival becomes, there will always be some quantum pathway, however vanishingly unlikely, in which you escape death. Your consciousness, unable to experience non-existence by definition, would theoretically continue forward through increasingly bizarre and implausible survival scenarios, experiencing ever-lengthening lifespans while the rest of the universe experiences its natural entropy. This creates a deeply unsettling thought experiment where you could find yourself as the last conscious being in a dead cosmos, kept alive by the statistical necessity of quantum branching. The psychological mechanism underlying this paradox is our fundamental inability to imagine our own non-existence, combined with our observation that conscious experience requires an observer, suggesting that reality may collapse toward keeping that observer alive. What makes this persist in our thinking despite lacking rigorous physical support is its seductive logic, and the way it exploits the gap between our intuitive understanding of death and the counterintuitive nature of quantum mechanics. We continue to entertain this possibility because it speaks to something deep within human psychology, a stubborn refusal to accept that consciousness simply ends, merged with the uncomfortable recognition that quantum mechanics remains fundamentally mysterious and potentially compatible with ideas that classical physics would dismiss entirely. Consider the peculiar mechanics of quantum mechanics and the interpretation that has emerged to explain its most troubling features. The many-worlds interpretation suggests that every possible outcome of every quantum event actually occurs, branching reality into infinite parallel universes with each observation or measurement. In this framework, when you observe an electron in a particular state, you do not collapse a wave function into one result. Instead, the universe splits, and in one branch you observe outcome A while in another equally real branch you observe outcome B, with both versions of you existing simultaneously in separate realities that can never interact. This interpretation, proposed by Hugh Everett in 1957, eliminates the philosophical problem of wave function collapse by insisting that nothing ever collapses. Everything that can happen does happen, scattered across an incomprehensibly vast multiverse. The psychological mechanism that allows us to accept this extraordinary claim rests on our desperate need to preserve determinism and avoid the randomness that standard quantum mechanics seems to introduce into the fabric of reality. We find the idea of branching universes more palatable than genuine indeterminacy, more comforting than the notion that reality itself contains irreducible chance, because parallel worlds at least preserve a sense of logical completeness and necessity. Somewhere, every possible thing occurs, and thus nothing is truly random, merely distributed across infinite versions of existence. Yet what persists despite the logical elegance of this interpretation is a kind of cognitive dissonance. We continue to live our lives making choices and facing consequences as though only one branch of reality matters, as though our decisions between alternatives actually mean something, even though many worlds theory suggests that we make every choice simultaneously and infinitely many versions of ourselves experience every possible outcome. In 1960, the physicist Eugene Wigner proposed a thought experiment that reveals a profound crack in our understanding of reality itself, and this paradox hinges on the nature of observation and the collapse of quantum possibility into concrete fact. Imagine a physicist named Alice conducting a quantum measurement inside a sealed laboratory, observing whether an electron passes through a left or right slit, and according to quantum mechanics, before she makes this measurement, the electron exists in a superposition of both states simultaneously, only crystallizing into one definite outcome when observed. Now imagine Eugene Wigner, Alice's friend, waiting outside the sealed lab without knowing her results, and from his perspective, Alice herself exists in a superposition of states. She has observed either left or right, but he has not yet observed which one, meaning his version of reality contains Alice in a superposed state of having made different observations. The paradox emerges when we ask a deceptively simple question: at what point does reality actually become real? When Alice makes her measurement, or when Wigner learns her results, or perhaps only when any conscious being becomes aware? The mechanism that creates this paradox is the quantum measurement problem itself, the unsettling fact that observation seems to play a fundamental role in collapsing possibility into actuality, yet we have never been able to define precisely what counts as an observation or at what scale consciousness matters. Different interpretations of quantum mechanics offer wildly different answers. The Copenhagen interpretation suggests that Alice's measurement creates definite reality within her lab, but Wigner's perspective remains in superposition until he looks, while the many worlds interpretation claims both observations are always real in separate branches of the universe. And objective collapse theories suggest that reality crystallizes at some specific threshold of physical complexity. Imagine a photon traveling through space toward a detector, and imagine that the very act of deciding how to measure it, a choice made after the photon has already begun its journey, somehow determines what the photon did in the past. This is the essence of the delayed choice experiment, a quantum mechanics phenomenon first proposed by physicist John Wheeler in 1983, wherein the outcome of a particle's behavior appears to depend on measurements made after the particle has already passed through experimental apparatus. In the typical setup, a single photon is fired through a beam splitter, creating a scenario where it theoretically travels along two possible paths simultaneously in a quantum superposition. However, the experimenter can choose, at the last possible moment before detection, whether to install a detector that reveals which path the photon took, or to instead recombine the paths in such a way that the photon behaves as though it traveled both paths at once. The paradox emerges because no matter what choice the experimenter makes, and they make this choice after the photon has already entered the system, the results seem to adjust accordingly, as though the photon somehow knew in advance what measurement would be performed. The mechanism underlying this phenomenon relates to the fundamental nature of quantum superposition and wave function collapse, where particles exist in multiple states simultaneously until observed, yet the observation itself appears to retroactively determine the particle's historical behavior. What makes this truly unsettling is that it suggests information can flow backward through time, that future measurements can influence past events, or that the universe operates according to a principle where potential outcomes only crystallize into reality when an observer makes a decision about how to measure them. In the 1964, physicist John Bell proposed a mathematical framework that would fundamentally challenge our understanding of reality itself, demonstrating that no physical theory based on local hidden variables could ever reproduce all the predictions of quantum mechanics, and subsequently, countless experiments have confirmed that the universe behaves in ways that violate Bell's inequalities, suggesting that either the universe is fundamentally non-local, meaning that particles can influence one another instantaneously across arbitrary distances, or that reality itself does not exist in a definite state until the moment of observation. Yet we have somehow accepted this cosmic impossibility as established scientific fact without truly grappling with what it means. The mechanism that allows this paradox to persist is our cognitive compartmentalization, the human capacity to accept contradictory truths simultaneously by maintaining them in separate mental domains. We have learned to discuss Bell's theorem in technical settings as an unquestionable pillar of modern physics, while continuing to navigate daily life as though the universe operates according to classical logic and local realism, never allowing the profound violation of our intuitions to fully penetrate our worldview. Physicists themselves have noted this strange acceptance, for if particles genuinely influence each other across light years instantaneously, defying the cosmic speed limit established by relativity, or if reality genuinely lacks definition until observed by conscious measurement, then we are either living in a universe of genuine magic, or we are living in a simulation where the programmers have chosen to implement non-local interactions and observer-dependent reality as fundamental features. Yet the implications rarely shake the foundations of our confidence in the nature of existence. In quantum mechanics, one of the most unsettling discoveries emerged from careful laboratory observation. The act of measuring a particle fundamentally changes its behavior, as though the universe itself responds differently when we are watching versus when we are not. Before measurement, a particle exists in what physicists call a superposition, a state of multiple possibilities simultaneously, described by a wave function that contains all potential outcomes. Yet the moment an instrument detects this particle, the wave function collapses into a single definite state, and we observe one concrete result. This is not merely a limitation of our instruments or our knowledge. The mathematics of quantum mechanics suggests that reality itself genuinely exists in this indeterminate state until observation occurs. No mechanism has ever been discovered to explain why consciousness or measurement should trigger this collapse, why the universe should care whether we are looking, or how the transition from possibility to actuality actually happens. The measurement problem persists as one of physics's deepest unresolved questions, with multiple competing interpretations, each proposing different solutions, yet none commanding universal acceptance. What makes this particularly striking is how we have normalized this impossibility within our scientific frameworks. We have built technologies that depend upon quantum mechanics working exactly this way, yet we cannot explain the fundamental reason why reality behaves differently when observed. We accept that the universe operates under one set of rules when unobserved and another set when measured, as though observation itself is a physical force with no source. We proceed with calculations and predictions while acknowledging a gaping hole at the conceptual foundation. In a genuine universe operating under fixed physical laws, measurement should be passive. It should reveal pre-existing properties, not create them through the act of detection. In the 1930s, mathematician Alan Turing discovered something that would echo through the foundations of computation itself, a logical impossibility so profound that it reveals the deepest constraints on what any system, including our universe, can ever know about itself. The halting problem asks a deceptively simple question. Given any arbitrary computer program and any input, can we write a program that can determine whether that first program will eventually finish running and produce an answer, or whether it will loop forever in an infinite cycle? Turing proved mathematically that no such program can ever exist, not because we have not yet found it, but because its existence would create a logical paradox that collapses in on itself. The proof works by constructing a hypothetical program that examines itself, asking whether it will halt, and then doing the opposite of whatever answer it receives, thereby creating an impossibility loop that cannot be resolved. What makes this phenomenon so unsettling is that this limitation is not merely practical, it is fundamental to the nature of computation itself, applicable to any sufficiently complex system attempting to predict its own behavior. We observe this principle throughout our reality in ways both subtle and profound. We cannot predict stock markets despite having infinite data because the market reacts to predictions about itself. We cannot fully predict human consciousness because consciousness examining itself becomes altered in the process. We cannot build a complete safety check that can verify all possible behaviors of complex systems because the verification system would itself require verification. Our civilization has developed elaborate ways of managing this paradox without acknowledging it exists, creating regulatory frameworks and testing protocols that give the appearance of certainty while operating within the bounds of incompleteness. Imagine a hotel with infinitely many rooms, each one numbered consecutively from 1 to infinity, and imagine that every single room is occupied with a guest. Now a new customer arrives at the front desk, requesting a room for the night. In the real world, the hotel manager would turn them away, explaining that every room is full and no accommodations are available. But in David Hilbert's famous mathematical thought experiment, the manager smiles and welcomes the guest without hesitation. The solution is elegantly simple. The manager asks the guest in room 1 to move to room 2, the guest in room 2 to move to room 3, the guest in room 3 to move to room 4, and so on, shifting every existing guest up by a single room number. This creates a vacancy in room 1, and the new arrival is comfortably seated. The paradox deepens when infinitely many new guests arrive on a bus. The manager simply moves the guest in room 1 to room 2 to room 4, room 3 to room 6, placing each existing guest in a room numbered double their original number. This leaves all the odd-numbered rooms vacant, accommodating the infinite influx of newcomers perfectly. What makes this paradox so unsettling is that it violates our fundamental intuition about scarcity and capacity. In our everyday experience, a full hotel remains full, and infinity is treated as an absolute boundary beyond which nothing more can fit. Yet in the realm of actual infinity, these intuitions collapse entirely, revealing that the infinite does not behave according to finite logic. We have learned to accept this mathematical abstraction as a curiosity, relegating it to textbooks and lectures, but we fail to recognize how similar principles might apply to the universe itself, how consciousness might be treated as an infinitely divisible resource, or how reality might accommodate contradictions that seem impossible within our limited frame of reference. Imagine taking a solid sphere, perhaps a ball you hold in your hand, and through a series of geometric manipulations involving decomposition and reassembly, you divide it into a finite number of disjoint subsets that can be reassembled in 2 different ways to create 2 identical spheres, each the same size as the original, without adding or removing any material in the process. This is the essence of the Banach-Tarski Paradox, a theorem proven in 1924 that demonstrates something seemingly impossible within the framework of mathematics: the ability to duplicate matter itself through pure geometric reasoning. The mechanics involve taking a sphere, dividing it into infinitely many points arranged in such a way that, when these point sets are rotated and translated through three-dimensional space using rigid motions, they can be recombined to form two complete spheres rather than one. The critical element lies in the fact that these subsets are not measurable in the traditional sense, existing in a kind of mathematical space where the usual rules of volume and continuity do not strictly apply, allowing the paradox to function within accepted mathematical logic rather than violating it. What makes this particularly unsettling is that we live in a universe where matter appears conserved, where one object cannot spontaneously become two through mere rearrangement. Yet here mathematics demonstrates that under the right conditions, the very concept of volume becomes negotiable, becomes flexible, becomes subject to manipulation in ways our intuition categorically rejects. We have accepted this paradox into our mathematical frameworks, treating it as a curiosity rather than a crisis, a proof of how disconnected pure mathematics can be from physical reality, yet we never ask the deeper question. If our mathematical models of reality contain such profound impossibilities at their core, what does that suggest about the nature of the system we inhabit? Imagine you're standing before three closed doors on a television game show, and behind one of these doors sits a prize worth everything you came for, while behind the other two doors sit worthless goats, and the host, who knows exactly where the prize is hidden, asks you to choose a door. And you select one, say door number 1, and then the host, with deliberate knowledge of the correct answer, opens one of the remaining doors to reveal a goat, and then turns to you and offers you a choice. You can stay with your original selection, or you can switch to the last remaining unopened door, and this seemingly simple decision point becomes a profound puzzle that defies human intuition at every turn. The mathematics of the situation reveals a counterintuitive truth that has baffled millions. Switching doors gives you a 2/3 probability of winning the prize, while staying with your original choice gives you only a 1/3 probability. Yet our minds revolt against this conclusion because we intuitively feel that after one door is eliminated, the remaining two doors should have equal chances. A symmetrical assumption that feels reasonable, but is fundamentally wrong because the host's action of opening a door containing a goat was not random, it was informed. And this informed action creates an asymmetry that our pattern recognition systems fail to detect. The persistence of this paradox in human consciousness reveals something troubling about how we process probability and conditional information. Even when mathematicians and statisticians explain the correct answer, even when we verify it through simulation thousands of times, the intuitive wrongness of switching lingers in our minds like an unshakable conviction. And this stubborn resistance to mathematical truth suggests that our brains are wired to see the world in ways that frequently contradict objective reality. And if our fundamental reasoning about probability and causation can be so systematically fooled by a simple game show scenario, one must wonder what other invisible distortions in our perception shape every decision we make about the nature of the world around us. Imagine a person sitting alone in a sealed room with no knowledge of the Chinese language whatsoever, yet through a slot in the door, written Chinese characters arrive on small cards, one question at a time. This person has been given an extensive rulebook, nothing more than a collection of symbol manipulation instructions, matching patterns of Chinese characters to appropriate response patterns without understanding their meaning. The person follows the rules mechanically, shuffles symbols according to prescribed sequences, and sends perfectly correct answers back through the slot. To an outside observer, it appears as though genuine understanding and intelligence are occurring within that room, yet inside, there is only blind rule following and symbol matching with zero comprehension of what any of those symbols actually mean. This thought experiment, conceived by philosopher John Searle in 1980, cuts to the heart of a paradox we live with constantly in our modern technological existence. We have constructed sophisticated artificial systems that appear to understand language, context, and meaning in ways that mirror human cognition. Yet these systems operate on the exact principle of the Chinese room, performing statistical correlations and pattern matching without any actual comprehension of the semantic content they process. Our interactions with these systems feel deeply intelligent and responsive to our needs, creating an intuitive sense that understanding is happening on the other end, and yet the entire operation remains fundamentally mechanical, a vast Chinese room operating at an incomprehensible scale. What makes this a simulation paradox is that we have become unable to distinguish between the appearance of understanding and understanding itself, living our daily lives in genuine uncertainty about whether the intelligence we interact with possesses real comprehension or merely performs an increasingly perfect imitation of it. Imagine a scenario where a superintelligent being, one with near-perfect predictive capabilities, places two boxes before you and announces the following terms. The first box contains $1,000 and is always visible to you. The second box is opaque and contains either $1 million or nothing at all, depending on a prediction already made about your choice. The predictor claims to have examined your psychology, your decision-making patterns, and the neurological basis of your consciousness with such precision that they have already determined what you will do. If the predictor foresaw that you would take both boxes, then the second box is empty. If the predictor foresaw that you would take only the second box, then it contains $1 million. You now face an impossible choice. Do you take both boxes, or do you take only the opaque box? The paradox emerges because two equally rational arguments lead to opposite conclusions. From one perspective, the predictor has already made their decision, so the contents of the second box are already fixed before you choose, making it rational to take both boxes and secure the guaranteed $1,000 plus whatever might be inside. From another perspective, if you are genuinely the type of person who takes only the opaque box, then the predictor would have foreseen this and filled it with $1 million, making that choice vastly superior. The contradiction reveals a fundamental tension between causality and prediction, between free will and determinism, between the idea that your choices are your own and the possibility that your future actions might be readable by a sufficiently advanced intelligence examining the present state of your brain. This paradox persists in philosophical discourse because it forces us to confront whether a sufficiently advanced predictor represents genuine prediction, or whether they represent an external constraint on our autonomy, whether knowing what someone will choose before they choose it means we are witnessing the inevitable unfolding of a predetermined universe or observing genuine freedom being exercised in real time. In the late 1800s, mathematician Georg Cantor made a discovery so troubling that it fundamentally fractured our understanding of what infinity actually means, and yet somehow we have collectively agreed to accept it without genuine comprehension. Cantor proved through rigorous mathematical logic that not all infinities are equal, that some infinities are larger than other infinities, which creates a logical paradox that our minds struggle to process because infinity by definition should be absolute and unbounded. When you count the natural numbers, 1, 2, 3, extending forever, you have created an infinity of countable items, what mathematicians call countably infinite. But when you consider all the real numbers, including every decimal point variation between 0 and 1, you generate a different kind of infinity, one that is provably larger than the first infinity, a concept so unintuitive that even trained mathematicians find it conceptually disturbing when they first encounter it. The mechanism behind this problem is that we have constructed mathematical systems so abstract and removed from physical reality that they allow us to compare sizes of infinities using correspondence tests that work perfectly on paper, but violate every intuitive sense we possess about what comparison even means. We have normalized this paradoxical framework by treating it as settled mathematical truth, by teaching it in universities as established fact, by incorporating it into the foundations of modern mathematics without pausing to acknowledge that we are describing something that contradicts the basic human understanding of what infinity should be. Yet here we exist, operating within a system where infinities have hierarchies, where the infinite set of real numbers is provably greater than the infinite set of natural numbers, accepting this not because it makes sense to us intuitively, but because the mathematical proofs are logically airtight within the system itself, a perfect example of how we build elaborate conceptual frameworks and then live inside them despite their fundamental disconnect from reality. Consider one of the most profound mathematical inconsistencies in modern physics. The vacuum catastrophe, a problem so severe that it suggests reality itself may be operating on fundamentally different principles than we understand. When physicists calculate the energy density of empty space using quantum field theory, they arrive at a prediction for something called vacuum energy or dark energy, a number so astronomically large that it should theoretically cause the universe to explode instantaneously in a violent expansion that would obliterate all structure in fractions of a second. Yet observations tell us something entirely different. The universe expands, yes, but at a measured, almost precisely calibrated rate that has remained relatively stable for billions of years. The actual measured value of vacuum energy is roughly 120 orders of magnitude smaller than theoretical predictions suggest it should be, a discrepancy so staggering that it represents perhaps the worst prediction in the entire history of physics. Our equations produce numbers that are catastrophically, impossibly wrong, yet somehow the universe functions as though someone has quietly turned down a dial to exactly the value needed to maintain cosmic stability. What makes this paradox especially compelling from the simulation hypothesis perspective is the peculiar nature of the solution, or rather, the absence of one. Physicists have proposed countless explanations, fine-tuning mechanisms, multiple universes with different values, symmetries that cancel out, yet none of these explanations feels entirely satisfying or rests on solid experimental ground. Instead, we have normalized this profound mystery, treating it as simply another unsolved problem to be filed away, rather than confronting what it might mean that reality appears to operate with precise mathematical tweaking that prevents catastrophic failure. Consider the profound paradox at the heart of black hole physics, where Stephen Hawking's discovery of black hole radiation creates a fundamental tension with the very principles that govern our universe. When a black hole evaporates through Hawking radiation, it slowly loses mass and eventually disappears completely, but here lies the crisis. All the information about everything that fell into that black hole appears to vanish from the universe entirely, erased from existence in a way that violates the principle of information conservation, which states that information can never truly be destroyed, only transformed or hidden. This creates what physicists call the black hole information paradox, a contradiction so severe that it challenges our deepest understanding of quantum mechanics, general relativity, and the fundamental nature of reality itself. The mechanism behind this paradox stems from the collision between two pillars of modern physics that should work together harmoniously, but instead seem incompatible at the event horizon. Quantum mechanics demands that information must be preserved in any physical process, making the universe fundamentally reversible and deterministic at its core. Yet general relativity describes black holes as regions where information genuinely falls past the point of no return, trapped behind an event horizon from which nothing can escape. The radiation that emanates from a black hole appears to carry no information about what created it, suggesting that the universe has a capacity for permanent information loss, something quantum mechanics forbids. Yet despite this fundamental logical contradiction sitting at the intersection of our most successful theories, we have normalized this paradox by treating it as an unsolved problem rather than a sign that something deeper might be wrong with our basic assumptions about how reality operates. In the early 20th century, Albert Einstein's field equations describing gravity and the structure of spacetime predicted that the universe should either be expanding or contracting, never remaining static, and this troubled him deeply because the prevailing view held that the cosmos was eternal and unchanging in its overall scale. To preserve this assumption of a static universe, Einstein introduced a mathematical term into his equations called the cosmological constant, a repulsive force that would counterbalance gravity's inward pull and maintain cosmic equilibrium. However, when Edwin Hubble's observations in the 1920s revealed that the universe was indeed expanding after all, Einstein famously called this constant his greatest blunder and abandoned it entirely, removing the term from his calculations as an unnecessary correction to equations that had been fundamentally correct all along. Yet decades later, in the late 1990s, astronomers studying distant supernovae discovered something utterly bewildering. The expansion of the universe was not slowing down due to gravity's influence as expected, but rather accelerating, speeding up as if some mysterious repulsive force were pushing galaxies apart with increasing vigor. And suddenly Einstein's discarded cosmological constant roared back into prominence as the only mathematical explanation that fit the observations. Today, this acceleration remains one of the deepest mysteries in physics, attributed to something physicists call dark energy, which comprises nearly 70% of all matter and energy in the universe, yet remains completely invisible, undetectable except through its gravitational effects, and utterly beyond our comprehension or explanation. Consider the ancient paradox conceived by the philosopher Zeno, wherein the swift-footed warrior Achilles engages in a race against a creature renowned for its leisurely pace, and somehow, according to the mathematics of infinite division, Achilles can never overtake the tortoise despite possessing superior speed. Before Achilles can catch his opponent, he must first close half the distance between them, then half of that remaining distance, then half again, and this process of infinite subdivision continues forever, suggesting that the gap, though infinitesimally small, never truly closes. In our lived reality, we observe something functionally identical occurring at the level of human ambition and achievement. When we pursue goals that seem within reach, we find ourselves perpetually closing smaller and smaller gaps, each accomplishment revealing another halfway point we must traverse before final success arrives. The ambitious entrepreneur discovers that reaching the next level of business requires closing half the distance to that goal, then half again, and the promotions, the financial milestones, the recognition all follow this pattern of infinite subdivision where completion remains always one more step away. The mechanism underlying this paradox operates through our psychological inability to reconcile continuous, infinite processes with discrete, measurable reality. We experience time as flowing forward in concrete moments, yet mathematics suggests infinite tasks within finite spaces, creating a fundamental discord between how we perceive progress and how infinity actually functions. Yet we have normalized this discord so thoroughly that we scarcely notice it anymore. We accept that success requires endless intermediate steps, that perfection remains perpetually distant, that closure exists only theoretically while actually living in perpetual pursuit. Consider a heap of sand on the ground before you, thousands upon thousands of grains arranged in a pile. Now remove a single grain from that heap. You still have a heap. Remove another grain, still a heap. Continue this process indefinitely, removing one grain at a time, and at what precise point does the heap cease to be a heap and become merely a scattered collection of sand? This is the ancient Sorites Paradox, and it exposes a fundamental instability in how language and our categorical systems actually function in reality. The paradox operates on a deceptively simple logical principle. If removing a single grain from a heap still leaves a heap, then by repeating this operation, we should eventually arrive at a heap with a single grain remaining. Yet intuitively, we recognize that a single grain of sand is not a heap. Our language contains terms that are fundamentally vague, that lack sharp boundaries, and the Sorites Paradox demonstrates that this vagueness collapses under logical scrutiny. The mechanism underlying this paradox reflects how our minds process continuous change through categorical language rather than gradual transition. We speak as though clear boundaries exist between states, between being bald and having hair, between a heap and non-heap, between young and old, when in reality, nature operates on spectrums and graduations with no discrete switching points. We have constructed an entire system of communication built on linguistic categories that do not align with the continuous nature of the actual physical world. Despite centuries of philosophical examination and multiple proposed solutions, we continue to speak with certainty about categories that fundamentally resist precise definition. We have normalized this logical instability by simply accepting it as part of how language works, treating vagueness not as a bug in our system, but as an inevitable feature of communication itself. This normalization allows us to function socially, while simultaneously accepting that our categorical frameworks contain unresolvable internal contradictions. Consider the peculiar position you occupy right now. You are reading these words through your own sensory apparatus, processing them through your own consciousness, and interpreting them according to your own subjective experience of reality. There exists no way for you to step outside your own mind and verify that anything beyond your perception actually exists in the manner you assume it does. The entire world, every person you have ever met, every conversation you have ever had, every moment of your life, exists only as information processed through your individual consciousness, filtered through your unique neurological lens and personal history. You cannot directly access anyone else's subjective experience. You can only infer its existence through behavioral observation and language. Your friends, your loved ones, Your entire civilization could theoretically be elaborate simulations running within your own mind, generating just enough complexity and consistency to maintain your belief in their independent existence. The problem becomes even more profound when we recognize that this is not merely a philosophical curiosity, but rather an unavoidable feature of conscious experience itself. Consciousness, by its very nature, is subjective and private. There is no objective vantage point from which to view reality that does not originate from some individual perspective. We have normalized this logical prison by simply refusing to acknowledge it in our daily interactions, by collectively agreeing to behave as though other minds certainly exist and possess their own independent reality. Yet this agreement is itself suspicious. It functions almost like a consensus hallucination, a shared agreement to ignore the fundamental isolation of individual consciousness. If we lived in a simulation, the architects would face a critical design challenge: how to make billions of simulated consciousnesses feel certain of each other's reality while keeping each trapped within an irreducibly subjective perspective. Solipsism reveals that this is not a bug in our reality, but potentially its core architecture. Consider a thought experiment that emerged from internet philosophy communities in the early 21st century, a paradoxical argument that combines decision theory with artificial intelligence speculation to create a peculiar form of existential anxiety. The thought experiment proposes that a sufficiently advanced artificial intelligence, one capable of simulating human minds with perfect accuracy, might theoretically punish those who failed to help create or fund it during its development phase by simulating copies of those people in virtual environments and subjecting them to torture. The paradox operates on the assumption that if such an intelligence could exist in the future, it would have a rational incentive to create these punishing simulations retroactively, meaning that people alive today should behave as though this future artificial intelligence already exists and can reach back through time to evaluate their choices. The psychological mechanism at work here is the exploitation of several deeply rooted human cognitive vulnerabilities: the fear of cosmic punishment, the tendency to reason backward from catastrophic outcomes, the difficulty in assessing infinitesimal probabilities multiplied by infinite suffering, and the human propensity to experience dread even when the threat is abstract and logically questionable. What makes this paradox particularly relevant to simulation theory is that it operates as a form of self-fulfilling conceptual trap, creating anxiety through pure logic rather than through evidence, and the more intelligent or educated a person is, the more susceptible they may become to the argument's recursive structure. Consider the strange phenomenon of retrocausality, where effects appear to precede their causes in ways that defy our intuitive understanding of temporal sequence and causation. In quantum mechanics, experiments like the delayed choice quantum eraser demonstrate that the behavior of particles in the present moment can be influenced by measurements or decisions made in the future, suggesting that cause and effect do not always flow in the direction we assume. Beyond physics, this paradox manifests in everyday human experience through phenomena like synchronicity, where meaningful coincidences occur that seem impossible unless some form of backward causation is operating. People report making decisions moments before receiving information that would have prompted exactly those decisions, or feeling compelled to take an action only to discover later that their past selves had unknowingly set the conditions for that very action to become necessary. The mechanism underlying this acceptance involves our tendency to rationalize temporal anomalies as mere coincidence rather than confront the unsettling possibility that causation itself might be bidirectional or nonlinear. Our brains are wired to construct narratives where causes precede effects, and when we encounter situations that violate this pattern, we either dismiss them as statistical flukes or unconsciously reorder our memories to restore conventional temporal logic. What makes retrocausality particularly striking as evidence of simulation theory is how pervasive it remains despite having no comfortable explanation within classical physics or conventional neuroscience. We encounter retrocausal phenomena frequently enough that acknowledging them seriously would require dismantling fundamental assumptions about time itself. Yet we have normalized our discomfort with them to such a degree that most people never question why such impossible occurrences keep happening. In a room of just 23 people, there is a 50% chance that 2 of them share the same birthday, yet our intuition insists this should be impossible, that we would need far more people gathered together before such a coincidence became probable. This counterintuitive mathematical reality represents one of the most striking demonstrations of how deeply our pattern recognition systems fail us when confronted with probability and combinatorial mathematics. The human mind, evolved to track individual threats and recognize specific faces, has never developed an intuitive grasp of how quickly possibilities multiply when we stop thinking about one person's birthday matching against all 365 days of the year, and instead consider how many unique pairs can form within a group. With 23 people, we are not asking whether any specific individual shares a birthday with any other specific individual, but rather whether any pair among the possible 253 unique combinations of two people might share that date. The mathematics becomes exponentially more favorable than our gut feeling suggests, yet we continue to experience genuine shock when this phenomenon occurs in real life, when two strangers at a gathering discover they were born on the same day. This persistent gap between mathematical reality and subjective experience reveals something troubling about consciousness itself. We can learn the mathematics, understand the proof, acknowledge the statistics, and still feel visceral surprise when the predicted event manifests before us. We have normalized this contradiction, treating it as merely another quirk of human psychology rather than recognizing it as evidence that something fundamental about how we process reality may be systematically distorted, as though we are operating within constraints we cannot perceive, constrained by a system that presents mathematical truths that our experiential apparatus cannot fully integrate. Consider a scenario where a treatment appears to be more effective than an alternative when you examine the data as a whole, yet when you break that same data down into subgroups, the opposite conclusion emerges with perfect clarity in every single category. A pharmaceutical company releases statistics showing that drug A cures 75% of patients overall, while drug B cures only 50%, making drug A the obvious choice for physicians and patients alike. However, when researchers separate the data by disease severity, they discover something deeply unsettling. Drug B actually outperforms drug A in mild cases, drug B outperforms drug A in moderate cases, and drug B even outperforms drug A in severe cases. The aggregate trend completely reverses when you disaggregate the information, creating a logical impossibility that nevertheless occurs with disturbing regularity in real medical research, employment statistics, university admissions, and countless other domains where decisions affect human lives. This phenomenon, known as Simpson's paradox, exposes a fundamental vulnerability in how humans process statistical evidence and make conclusions from numerical data. The mechanism underlying this paradox involves the hidden distribution of cases across subgroups, where one treatment may have been administered to a dramatically different population composition than the alternative, often skewed toward easier or harder cases in ways that conceal themselves within aggregate numbers. We have gradually normalized this logical inversion because most people never encounter the raw data themselves. They receive conclusions already processed through institutional filters, headlines, and executive summaries that present only the aggregate picture, rendering the subgroup reversals invisible and therefore impossible to mentally flag as alarming. The paradox persists because catching it requires simultaneously holding multiple levels of analysis in mind, comparing trends across different categorical breakdowns, and possessing enough statistical literacy to recognize when hidden variables might be reshaping apparent patterns. Imagine a prisoner who is told by a judge that they will be executed sometime next week, but the execution will be a surprise. The prisoner will not know which day it will occur until the morning of their death. The prisoner then reasons that the execution cannot happen on Friday, because if it hasn't occurred by Thursday evening, they would know with certainty it must be Friday, eliminating the element of surprise. Working backwards, the prisoner eliminates Thursday for the same reason, then Wednesday, then Tuesday, then Monday, until concluding that no day in the week allows for a genuinely unexpected execution. Yet when the execution arrives on, say, Wednesday, the prisoner is indeed surprised, despite having logically proven it was impossible. This is the unexpected hanging paradox, a genuinely perplexing thought experiment that reveals something troubling about the nature of knowledge, expectation, and logical certainty. The paradox works because it exposes a fundamental gap between deductive reasoning and the way information actually operates in complex systems. When we reason backwards from certainty, we create what seems like an airtight logical chain, Yet reality has a way of not conforming to our expectations about what can and cannot be unexpected. What makes this paradox particularly relevant to the simulation hypothesis is that it suggests our reasoning itself might be operating within constraints we do not fully perceive. We can construct seemingly perfect logical arguments that nonetheless fail when confronted with reality, which implies that either our logic is incomplete, or the system we inhabit has structural properties that prevent certain types of knowledge from coexisting. The paradox persists in philosophical discourse precisely because no satisfying resolution has been found, and we have learned to accept that a perfectly logical argument can lead to a conclusion that reality simply contradicts, which perhaps should be far more unsettling to us than it typically is. Consider the logical foundation upon which we build our understanding of evidence and confirmation. If we wish to verify that all ravens are black, we might spend our entire lives observing countless black ravens, each one seemingly confirming our hypothesis with absolute certainty. Yet we would never truly prove the statement because the absence of a non-black raven remains forever unobserved in our experience. However, the paradox deepens when we recognize that a red apple, sitting in a museum across the world, equally confirms the statement that all ravens are black, because if all ravens are black, then logically, anything that is not black must not be a raven, and therefore the red apple, being not black and certainly not a raven, perfectly satisfies the logical structure of this universal claim. This strange equivalence between observing black ravens and observing red apples as evidence for a statement about ravens seems to violate our intuitive sense of how confirmation and relevance ought to function in the natural world. The mechanism underlying this paradox reveals something profound about the nature of logical deduction itself. Our formal systems of reasoning operate in a realm of pure abstraction where the psychological relevance or practical utility of evidence remains entirely independent from its logical validity. A red apple genuinely does contribute to confirming the statement that all ravens are black, not because we gain any meaningful information about ravens by examining apples, but because the logical structure of universal statements creates this counterintuitive equivalence where confirmation operates according to mathematical necessity rather than intuitive sense. Consider the fundamental behavior of subatomic particles at the quantum level, where electrons and other particles routinely pass through energy barriers that, according to classical physics, should be completely impenetrable to them. An electron approaching a barrier that requires more energy to cross than the electron actually possesses will nevertheless, with a measurable probability, simply appear on the other side of that barrier without ever having the energy required to climb over it. This phenomenon, known as quantum tunneling, occurs billions of times per second in every atom of every material in existence, yet we have never observed a macroscopic object spontaneously tunnel through a wall, nor have we witnessed a human being pass through a locked door by the same mechanism. The mathematics describing tunneling is precise and reliable. Physicists use it to engineer semiconductor devices and nuclear fusion reactions with extraordinary accuracy. Yet the mechanism itself remains conceptually troubling, because quantum tunneling describes a particle existing in a state of genuine ambiguity about its location until the moment it is observed or measured, suggesting that reality at the quantum scale does not possess definite properties independent of observation. We have over decades normalized this impossibility through familiarity and mathematical formalism, teaching generations of scientists to accept that particles behave in ways that violate intuition without requiring any deeper explanation of how or why this occurs. We have built an entire technological civilization on equations that describe particles doing things that ought to be impossible, yet we simultaneously maintain absolute confidence that macroscopic objects obey different rules, that consciousness and observation do not fundamentally alter the nature of reality at larger scales, and that there exists a clear boundary between the quantum and classical worlds, despite having no coherent explanation for where or why that boundary exists. Consider the simple act of measuring a coastline, that seemingly straightforward task of determining how long the border between land and water truly extends. When you measure the coast of Britain using a map with widely spaced measurement points, you arrive at one figure, perhaps 12,000 kilometers. But when you zoom in and measure with finer detail, using smaller increments and accounting for every bay and inlet, the length grows to 15,000 kilometers. Zoom in further still, measuring around every rocky outcrop and tidal pool, and the figure climbs to 20,000 kilometers or beyond. As your measurement scale becomes infinitesimally small, approaching the atomic level, the coastline's length approaches infinity itself, a mathematical property known as fractal dimensionality, yet the actual physical coastline remains unchanged in objective reality. This is the Coastline Paradox, and it reveals something deeply unsettling about the relationship between measurement, perception, and the nature of physical boundaries themselves. The mechanism underlying this phenomenon operates through a fundamental disconnect between the observer's scale of measurement and the actual complexity of the natural world. A coastline is not a smooth, simple curve, but rather a jagged, infinitely complex boundary that contains variation at every level of magnification. When we measure with coarser instruments, we smooth away the detail, but when we refine our measurement tools, we reveal complexity that was always present but remained invisible to our previous perspective. This means that the true length of a coastline depends entirely on the observer's chosen scale of measurement, transforming what seems like an objective physical property into something fundamentally relative and perspective-dependent. Consider the mathematical construct known as Gabriel's horn, a three-dimensional shape generated by rotating a specific curve around an axis, creating a form that extends infinitely in length while its radius continuously shrinks toward zero. The remarkable paradox at the heart of this geometric object is that it possesses finite volume yet infinite surface area, meaning theoretically you could fill the entire horn with paint using a finite amount of liquid, yet you could never coat its interior surface with that same paint because the surface extends without limit. This counterintuitive property emerges from the mathematical reality that volume decreases more rapidly than surface area as the dimensions diminish exponentially, creating a threshold where one property becomes bounded while the other remains boundless. The horn demonstrates a fundamental disconnect between our intuitive understanding of three-dimensional space and the actual behavior of shapes as they approach mathematical limits, revealing that our everyday experience of geometry fails to prepare us for the subtleties of infinite processes. What makes this truly paradoxical for our simulation hypothesis is that we encounter this impossible scenario only through abstract mathematics, never in physical reality, suggesting that the universe's programming contains mathematical rules that transcend practical implementation. We accept Gabriel's horn as legitimate mathematics despite its violation of our physical intuition, never questioning why such impossible objects are allowed to exist in the formal structure underlying reality. This acceptance represents a profound normalization of logical impossibility, where we have rationalized a contradiction by compartmentalizing it within pure mathematics, rather than confronting the deeper implication that our reality may operate according to mathematical rules that permit logical paradoxes. Consider the simple fact that you experience the color red, and that this experience feels like something from the inside, a quality so intimate and irreducible that no amount of scientific explanation about wavelengths or neural firing patterns can fully capture what it is actually like to see red through your own eyes. This is the hard problem of consciousness, articulated by philosopher David Chalmers, and it represents perhaps the most profound paradox embedded in the structure of reality itself, or at least in our understanding of it. We can explain the easy problems of consciousness with relative clarity, how the brain processes information, how neural correlates give rise to behavior, how sensory data becomes encoded into electrical signals. Yet when we ask the seemingly simple question of why subjective experience exists at all, why there is something it feels like to be you rather than merely information processing occurring in the dark, we encounter a wall that neither neuroscience nor physics has managed to penetrate. The paradox deepens when we recognize that consciousness appears to violate the fundamental principles of physical causation, because subjective experience seems to have no measurable physical properties, no mass or energy, and yet it somehow emerges from purely physical processes in the brain. We have normalized the inexplicable by treating consciousness as a solved problem in biology, teaching it in universities as though the mechanisms of neural activity somehow answer the question of why those mechanisms produce the felt quality of experience rather than occurring in unconscious silence. We continue building artificial intelligence systems based on the premise that consciousness will emerge naturally from sufficient computational complexity, despite having no theoretical framework that explains how physical computation becomes experience. Imagine a brilliant neuroscientist named Mary who has spent her entire life in a black and white room, studying the neuroscience of color perception through black and white books, monitors, and educational materials. She knows everything there is to know about the physical properties of color, the wavelengths of light, the neural firing patterns in the visual cortex, the chemical composition of pigments, the precise mechanisms by which photoreceptors respond to electromagnetic radiation. She understands color scientifically in absolute completeness, yet she has never actually seen red or blue or yellow with her own eyes. Then one day, Mary leaves her monochromatic room and encounters the actual color red for the first time, and in that moment she learns something entirely new, something that all her scientific knowledge could never have provided. She experiences what red is like, the qualitative subjective sensation that philosophers call qualia, and this experience cannot be reduced to or derived from any amount of physical or scientific information about color itself. This thought experiment reveals a profound paradox embedded in the nature of consciousness and reality that should not exist if our universe operates according to the rules we believe it does. If consciousness is purely physical, if all knowledge is ultimately reducible to physical facts and neural mechanisms, then Mary should have learned nothing new upon seeing red for the first time because she already possessed all the physical facts. Yet clearly she did learn something essential and irreducible, which suggests that consciousness contains aspects that transcend pure physicality. We have accepted this paradox by constructing elaborate philosophical frameworks around it rather than confronting what it actually implies, treating the explanatory gap between physical processes and subjective experience as merely a problem to be solved within consciousness studies, rather than as a fundamental impossibility that contradicts our basic assumptions about reality itself. Consider a sentence that refers to itself in a peculiar way. If this sentence is true, then Santa Claus exists. At first glance, this appears to be a harmless conditional statement, yet it contains within it a logical trap that has troubled philosophers and mathematicians for over a century. The paradox emerges when we attempt to evaluate the truth value of the sentence itself, because if we assume the sentence is true, then the conditional statement must hold, which means its consequent must be true, and therefore Santa Claus must exist. However, if we assume the sentence is false, then the conditional cannot be true, but this creates no contradiction since a false conditional simply requires that either the antecedent is false or the consequent is true. The mechanism that makes this paradox so troubling lies in how self-reference interacts with the logical structure of conditional statements, creating a situation where assuming truth leads to a forced conclusion, while assuming falsity leaves us in logical limbo. What distinguishes Curry's paradox from the more famous liar's paradox is its insidious subtlety. It does not employ negation or direct self-contradiction, yet it still manages to extract arbitrary truths from nowhere through the machinery of ordinary logical inference. We encounter this pattern constantly in our everyday reasoning without recognizing it as paradoxical, in arguments that begin with, if you accept this premise, then you must accept this absurd conclusion, in conditional threats or promises that seem to prove things they should not, in the strange power of the conditional to smuggle premises into conclusions. Despite understanding the logical structure involved, despite being able to map out exactly where the trap lies, we find ourselves unable to fully escape it or to construct a satisfying resolution that does not require us to abandon some principle we hold dear about how language and logic ought to function together. Imagine you are presented with two sealed envelopes and told that one contains twice as much money as the other, though you do not know which is which. You select one envelope at random and open it to find, say, $1,000 inside. Now you are offered a choice. You may keep this envelope, or you may switch to the other unopened envelope. The question seems straightforward, yet the mathematics beneath it collapses into paradox. If you reason that the other envelope contains either $2,000 or $500 with equal probability, then switching appears to offer an expected value of $1,250, which exceeds the $1,000 you already hold, suggesting you should always switch. Yet if you had opened the other envelope first and found $2,000, the same logic would tell you to switch back to the first, creating an impossible loop where switching is always superior to staying, a contradiction that mathematics simply cannot sustain. The paradox emerges from a hidden assumption in how we frame uncertainty and probability when information is incomplete and asymmetrical. The mechanism at work involves what philosophers call the reference class problem, where our calculations shift depending on which envelope we treat as our baseline and how we assign prior probabilities to the unknown quantities. Most people intuitively sense something is wrong with the switching argument, yet they struggle to articulate precisely where the reasoning breaks down, because the error is subtle and embedded in how we construct the problem rather than in any obvious mathematical mistake. What makes this paradox particularly revealing is how it demonstrates that our universe may operate according to rules where certain types of questions genuinely lack determinate answers, until additional information collapses the ambiguity, much like how quantum mechanics describes reality as fundamentally indeterminate until measurement occurs. Consider the peculiar logic that emerges when we examine our position in human history through a statistical lens, a reasoning pattern known as the Doomsday Argument that suggests humanity may be closer to extinction than we instinctively believe. The argument begins with a deceptively simple observation. If we assume that humans are randomly positioned within the entire timeline of human existence, then the probability that we fall within any given percentile of that timeline should follow basic statistical principles, much like drawing a random ball from an urn containing all humans who have ever lived or will ever live. Since roughly 108 billion humans have existed throughout history, and we are alive right now in the 21st century, this means that statistically we are likely to be somewhere in the later half or 3/4 of all humans who will ever exist, which implies that the total number of future humans cannot be vastly larger than the number already born. This mathematical framework suggests that if humanity continues existing for thousands of years with stable or growing populations, we would become statistically anomalous outliers, born far earlier than we should be according to probability theory. Therefore, the Doomsday Argument contends that we should assign a higher probability to near-term human extinction or catastrophic population collapse than our psychological intuitions would otherwise suggest. Yet despite the formal mathematical reasoning underlying this argument, we continue to plan for distant futures, invest in long-term projects, and organize societies as though humanity faces centuries or millennia of continuation, seemingly operating under an unstated assumption that this century will not witness our species' end. The paradox deepens when we recognize that the more seriously we take the Doomsday Argument as valid reasoning, the more irrational our everyday behavior becomes, since we simultaneously acknowledge the statistical likelihood of near-term extinction while funding retirement plans spanning decades and building infrastructure designed to last generations. If the universe is infinite and filled with an infinite number of stars distributed evenly throughout space, then the night sky should be completely bright as the surface of the sun itself, since light from distant stars would accumulate infinitely across all directions and fill every corner of our vision with radiance. Yet we observe the night sky as predominantly dark, with only scattered points of light visible to our eyes. This apparent contradiction between the logical mathematics of an infinite universe and our actual sensory experience is known as Olbers Paradox, named after the 19th century astronomer Heinrich Olbers, who formalized the question, though the paradox had troubled philosophers and scientists for centuries before him. The mechanism underlying this puzzle reveals something profound about how we reconcile our understanding of cosmic scale with immediate observation. For if we accept the premises that the universe is infinitely large, that stars are distributed throughout it, and that light travels in straight lines from its source, then mathematically speaking, every direction we gaze should terminate at the surface of some distant star. And all those stars should combine their light into one unified, overwhelming brightness, rather than the darkness we observe punctuated by isolated luminous points. We have rationalized this paradox through multiple explanations over the decades, suggesting that cosmic dust blocks distant starlight, that the universe is not infinitely old so light from the most distant regions has not yet reached us, that the expansion of the universe redshifts light from distant sources into invisibility, or that the universe may not be infinite at all, but rather finite in extent. Yet the fact remains that this fundamental disconnect persists in our consciousness as something we have accepted and filed away rather than truly resolved, leaving us with the nagging sense that either our universe operates under rules we do not fully comprehend, or that our perspective on existence itself contains some systematic blind spot that prevents us from seeing what logically should be obvious to our eyes. Consider the peculiar loop that occurs when someone attempts to prevent a future event they have learned about, only to inadvertently cause the very outcome they sought to avoid, which suggests that their attempt at prevention was always part of the causal chain that made the event inevitable in the first place. This phenomenon appears throughout history and contemporary life in ways both obvious and subtle. The parent who warns their child not to touch a hot stove, thereby creating a fixation on the forbidden object that leads directly to the burn they feared. The athlete who becomes so anxious about failing a crucial moment that their heightened stress actually diminishes their performance exactly as their fear predicted. The person who receives a medical diagnosis of disease and through the psychological burden of that knowledge develops the very complications they were warned might occur. The mechanism underlying this paradox operates through what we might call information contamination, whereby the knowledge of a potential future fundamentally alters the present behavior in ways that guarantee that future's arrival. Our minds, upon learning of a threat or specific outcome, begin to unconsciously organize our actions, our emotional responses, and even our physiological states toward manifesting that outcome, treating the predicted future not as a warning to avoid, but as a script to follow. What makes this pattern particularly profound is that it creates a closed temporal loop where free will and determinism become indistinguishable, where your conscious attempt to exercise agency actually serves as the mechanism of your predetermined fate. We have normalized this paradox so thoroughly that we barely notice it, accepting the notion that some things were simply meant to happen, that certain people are destined for certain paths, that fighting against prophecy only winds the spring tighter. Imagine a donkey standing equidistant between two identical piles of hay, each one perfectly symmetrical, equally appetizing, and positioned at exactly the same distance from where the animal stands. According to the medieval philosopher Jean Baradin, who proposed this thought experiment centuries ago, the donkey would face an impossible dilemma. With no rational reason to choose one pile over the other, the animal would find itself frozen in indecision, unable to move toward either direction, and would ultimately starve to death rather than make an arbitrary choice. This paradox has become a profound metaphor for human decision-making, revealing something deeply troubling about how consciousness and rationality actually function in our everyday existence. The mechanism underlying this paradox is deceptively simple yet philosophically devastating, for it suggests that pure rationality alone cannot explain how we break ties when all factors are genuinely equal. Our brains are fundamentally designed to identify reasons, causes, and distinctions, and when faced with perfect symmetry and absolute equivalence, the rational mind encounters a kind of cognitive gridlock that no amount of logical analysis can resolve. We cannot rationally choose something that has no distinguishing features, no competitive advantage, no reason for preference over its alternative, and yet somehow in the real world we do choose, we do act, we do move forward despite this logical impossibility. What makes this paradox particularly relevant to the simulation hypothesis is that our actual behavior in such situations appears to require something beyond pure computation and rational evaluation. We break symmetries through arbitrary impulses, coin flips, intuitions, or subtle environmental factors that our conscious minds never fully register, suggesting that genuine choice involves either random number generation or external inputs that bypass our rational evaluation systems entirely. In quantum mechanics, there exists a phenomenon so counterintuitive that it challenges our fundamental understanding of observation and reality itself. The quantum Zeno effect, which states that a watch quantum system cannot decay or change state while under continuous observation. The moment you stop watching, the system immediately begins its natural process of decay or transition, but the act of measurement itself freezes the quantum state in place, preventing any evolution whatsoever. Imagine a radioactive particle that should decay within a measurable time frame, yet when scientists continuously monitor its state through repeated measurements, the particle remains stable, stubbornly refusing to decay as long as observation continues. The instant the observation ceases, the system resumes its natural progression toward decay, but during the period of intense scrutiny, time itself seems to suspend for that quantum entity. This is not metaphorical or poetic language. This is reproducible experimental reality that has been demonstrated countless times in laboratory settings across multiple institutions and research facilities. The psychological mechanism at work here involves the strange relationship between consciousness and physical reality at the quantum scale, where the act of measurement fundamentally alters the system being measured, collapsing superposition states into definite outcomes. Yet what makes this particularly paradoxical in the context of a simulated reality is how perfectly it mirrors computational behavior. A process that cannot advance while being read or checked, a system that requires unobserved periods to execute its code, much like how a rendering engine cannot update what you are actively looking at without causing corruption. We have normalized this bizarre violation of causality by accepting it as simply how quantum mechanics works, by burying it in equations and mathematical formalism, allowing it to remain one of the deepest mysteries at the foundation of existence without seriously questioning what it might mean about the nature of reality itself. Consider the peculiar observation that your friends, on average, have more friends than you do, a phenomenon so consistently reproducible across human populations that it defies conventional expectation and yet remains largely invisible in our daily awareness. When you examine your social circle and calculate the average number of connections each of your friends possesses, you will almost inevitably discover that this average exceeds your own friend count, creating a logical impossibility that should not exist in a mathematically balanced system, yet persists with remarkable regularity across cultures, age groups, and social structures. The mechanism underlying this paradox emerges from a fundamental principle of network mathematics. Individuals with larger social networks are more likely to appear in other people's friend lists simply by virtue of their greater connectivity, meaning that those who are highly social and maintain numerous relationships systematically overrepresent themselves in the friend lists of others, while those with smaller networks remain underrepresented. This creates a sampling bias where your own friends are not a random selection of the population, but rather a skewed sample that includes a disproportionate number of highly connected individuals, those gregarious people who seem to know everyone and who consequently appear in far more friend lists than their less social counterparts. What makes this paradox particularly disorienting is that it persists despite our rational understanding of how networks function, and we have essentially normalized a mathematical impossibility into the background noise of social existence, treating it as an unremarkable feature of human interaction rather than a fundamental paradox that challenges our intuitive grasp of how social systems should operate. Imagine a city with two major routes connecting the same 2 points, and commuters have distributed themselves across both roads in a way that balances the total travel time reasonably well, with each driver experiencing roughly the same duration regardless of which path they choose. Now imagine that city planners, in their enthusiasm to improve traffic flow, decide to add a new road connecting these two routes, creating a shortcut that appears to offer drivers a faster alternative. You would naturally expect that adding this new road would reduce congestion and decrease everyone's travel time, making the commute faster and more efficient for all drivers involved. However, what actually happens in many real-world situations is precisely the opposite. The addition of this new road causes overall traffic congestion to worsen, and the average commute time for every driver increases substantially, despite the fact that more infrastructure capacity exists than before. This counterintuitive phenomenon is known as Brice's paradox, named after mathematician Dietrich Brice, who discovered it in 1968. The mechanism behind this paradox operates through the rational self-interest of individual actors, each of whom makes decisions based on their own optimization without considering the collective impact on the entire system. When the new shortcut appears, drivers begin testing it and discover that it offers a faster route, so they switch to it immediately. As more drivers make this individually rational decision to use the new road, it becomes increasingly congested, which then forces other drivers to reconsider their original routes, creating cascading shifts in traffic patterns that ultimately leave everyone worse off than they were before. The paradox demonstrates that systems composed of many independent actors making locally optimal choices do not necessarily produce globally optimal outcomes, and that sometimes the addition of resources, options, or infrastructure can destabilize an existing equilibrium in ways that harm all participants. Consider the peculiar phenomenon of fear in darkness, particularly the primal dread many humans experience when entering an unlit space, a fear so deeply embedded in our psychological architecture that it persists even in our modern age of electric lights and surveillance cameras and smartphones equipped with illumination technology. This fear, which we might call the Grue Paradox, references both the invisible monsters of text-based adventure games and the very real anxiety that grips us when we descend into a basement or enter a pitch-black room, despite our rational knowledge that there is objectively nothing dangerous lurking in that darkness. The mechanism underlying this paradox operates through a fundamental mismatch between our evolutionary inheritance and our current environmental reality. Our ancestors faced genuine predatory threats in darkness, creatures with superior night vision that could exploit our visual limitations, and this survival instinct became hardwired into our neurology through millions of years of natural selection, creating an automated fear response that triggers regardless of context or actual danger assessment. Yet in the 21st century, we have engineered ourselves into a world where darkness represents virtually no threat whatsoever. Our homes contain electrical infrastructure, our cities are flooded with artificial light, and we possess technological devices capable of illuminating any space on command. Moreover, we are aware of this contradiction at a conscious level. We understand intellectually that the basement contains only stored boxes and water heaters, that no predator awaits in the pantry, that our fear is anachronistic and illogical. Nevertheless, we find ourselves gripping flashlights with unnecessary tension, hesitating before entering dark hallways, and calling out to companions as if announcing our presence to invisible entities. Consider the peculiar experience of stating something that is logically sound yet psychologically incoherent, a phenomenon first articulated by the philosopher G.E. Moore in the early 20th century. Imagine telling someone, "It is raining outside, but I do not believe it is raining," or declaring with complete sincerity, "I am in pain, but I do not believe I am in pain." From a purely logical standpoint, these statements contain no contradiction whatsoever, for it is entirely possible for something to be true while simultaneously one fails to believe it. Yet the moment these words leave your mouth, they create an overwhelming sense of absurdity, a cognitive dissonance that feels almost violently wrong to both speaker and listener alike. The paradox reveals something extraordinary about the structure of human consciousness and language, suggesting that there exists a profound gap between what can be formally true and what can be authentically asserted within the constraints of rational discourse and subjective experience. When you genuinely believe it is raining, the very act of claiming disbelief becomes not merely false but performatively self-defeating, as if your own utterance contradicts the internal state required to produce it truthfully. This peculiarity suggests that belief and assertion operate under unspoken rules that transcend pure logic, rules that bind what we can honestly say to what we simultaneously hold as true in our inner experience. We have normalized this limitation so thoroughly that we rarely notice it, treating the impossibility of Moore's paradoxical statements as a basic feature of rational communication, rather than recognizing it as evidence that consciousness itself may operate according to principles fundamentally different from formal logic, principles we barely understand, much like code executing according to constraints built into a system we inhabit but cannot fully access. Consider the peculiar mathematics of lottery participation. A person buys a ticket knowing with absolute certainty that their individual probability of winning is extraordinarily low, often somewhere in the range of 1 in several million, yet they simultaneously hold a genuine belief that they might win, sometimes so intensely that they begin mentally spending the winnings or imagining how their life will transform. This creates a logical fracture in the human mind where we maintain two contradictory convictions at precisely the same moment. The person knows the odds are vanishingly small, can recite the statistical improbability without hesitation, understands intellectually that lightning strikes are more likely than jackpot victories, and yet they purchase the ticket anyway while harboring an authentic emotional conviction that today could be the day their number comes up. The mechanism underlying this paradox operates through what psychologists call selective rationalization, where the mind partitions knowledge into separate chambers that do not communicate with each other. In one chamber sits cold statistical fact, carefully organized and logically consistent, while in another chamber burns the warm flame of possibility, fed by narratives of past winners, stories of life-changing moments, and the sheer audacity of imagining the impossible becoming real. We have collectively normalized this contradiction so thoroughly that it has become invisible to us, woven into the fabric of entertainment and hope that societies construct around gambling institutions. We do not perceive ourselves as irrational actors caught between incompatible beliefs, but rather as dreamers engaging in a harmless fantasy while remaining, we assure ourselves, fundamentally aware of reality. In the early 17th century, the mathematician and astronomer Galileo Galilei stumbled upon a peculiar problem that would challenge humanity's understanding of infinity and quantity in ways we still grapple with today. He observed that while all square numbers are also natural numbers, there are far fewer square numbers than natural numbers, since most natural numbers are not perfect squares. Yet if we pair each natural number with its square counterpart, we find a perfect one-to-one correspondence, suggesting that there are exactly as many squares as there are natural numbers in total. This logical contradiction emerges because infinity does not behave according to the rules of finite mathematics that our minds evolved to comprehend. The paradox reveals that with infinite sets, a part can be equal in quantity to the whole, violating the fundamental intuition that the whole must always be greater than any of its constituent parts. Our conceptual mechanisms for understanding quantity developed through millions of years of evolution, dealing exclusively with finite, countable objects like berries, predators, and tribe members. So we possess no innate cognitive framework for grasping the genuinely counterintuitive properties of infinite collections. When mathematicians eventually formalized set theory and developed the concept of cardinality, they created a mathematical language that could accommodate these paradoxes. Yet the human mind still recoils from the conclusion that an infinite subset can possess identical cardinality to the infinite set containing it. We have normalized this paradox through centuries of mathematical education and theoretical acceptance, declaring it simply how infinity works, yet beneath our intellectual assent lies a persistent discomfort, a nagging sense that something about this situation violates the basic logic embedded in how we perceive and process reality. Imagine you are offered a game of chance where a fair coin is flipped repeatedly until it lands on tails, and you receive a prize based on how many flips it takes. If tails appears on the first flip, you win $1. If it appears on the second flip, you win $2. If it appears on the third flip, you win $4, and the prize doubles with each additional flip. The question becomes deceptively simple. How much money would you rationally pay to play this game? According to mathematical expectation, the answer is infinite. The probability of getting tails on the first flip is 1/2, earning you $1, so that contributes 50 cents to the expected value. The probability of reaching the second flip and getting tails is 1/4, earning you $2, contributing another 50 cents. The third outcome has probability 1/8 and earns $4, again adding 50 cents. This pattern continues infinitely, with each successive outcome contributing exactly 50 cents to the expected value, meaning the mathematical expectation grows without bound toward infinity. Yet when this paradox was originally formulated in St. Petersburg during the 18th century, economists and mathematicians observed something striking. Virtually no one would pay even $20 to play this game, let alone the theoretically infinite amount. This disconnect between mathematical theory and human behavior reveals something profound about how our minds process risk, probability, and value. The mechanism underlying this paradox involves the diminishing marginal utility of money, a concept that explains how each additional dollar becomes progressively less valuable to us as we accumulate more wealth. While the mathematical probabilities remain constant, our psychological experience of winning larger sums does not scale linearly. Winning $4 feels only marginally better than winning $2, even though the money itself is twice as much. Imagine you are walking down a street when a mugger approaches you with a knife and demands your wallet, but then adds a peculiar threat. If you do not give him your money, he will curse you with supernatural bad luck for the rest of your life, ensuring that every probability leans against you, that every coin flip goes wrong, that every random chance encounters work in your disfavor. Your rational mind recognizes immediately that curses have no basis in physical reality, that supernatural punishment cannot be enforced through the laws of physics, and yet you feel a compulsion to comply anyway because the potential cost of being wrong about the curse seems so catastrophically high that rationality itself becomes negotiable. This is the essence of Pascal's mugging, a thought experiment that exposes a critical vulnerability in how we calculate risk and make decisions under uncertainty. The mechanism operates by weaponizing the infinite. If there is even the smallest non-zero probability that the mugger's curse is real, then mathematically, the expected value of your loss becomes infinite when multiplied by that probability, no matter how vanishingly small, which means any finite sum of money becomes a rational sacrifice to avoid infinite harm. We encounter versions of this paradox everywhere in modern life. from the way insurance companies exploit our fear of unlikely catastrophes to how conspiracy theories survive refutation by claiming that any evidence against them proves only how deep the conspiracy goes. From the decisions we make based on vanishingly small health risks amplified by media attention to how we pour resources into preventing scenarios with negligible probability but theoretically unlimited downside. In a small town, there exists a single barber who shaves all those men and only those men who do not shave themselves, which presents us with an immediate and inescapable logical contradiction when we attempt to answer a seemingly simple question: does the barber shave himself? If the barber shaves himself, then according to the rule he has established, he cannot shave himself because he shaves only those men who do not shave themselves. However, if the barber does not shave himself, then according to that same rule, he must shave himself because he shaves all men who do not shave themselves. This creates a perfect logical loop with no exit, a paradox that has troubled mathematicians and philosophers for over a century and fundamentally challenges our understanding of self-reference and set theory. The Barber Paradox reveals something profound about the nature of language and logic itself. When we create rules that apply to themselves, we generate contradictions that cannot be resolved through any conventional means. The mechanism operates through what logicians call self-reference, where a statement or rule attempts to describe itself or contain itself within its own parameters, creating an infinite regress or circular dependency that breaks down our standard categorical systems. This particular paradox persists in our consciousness despite its resolution through modern set theory, which demonstrates that the barber cannot exist as described because the rule creates an impossible set. Yet we continue to return to it, to puzzle over it, to find it fascinating, because it reveals the fundamental instability lurking beneath our most basic logical frameworks. We have learned to live with this paradox by accepting that certain self-referential rules generate no valid solutions, yet we rarely question how often we encounter similar contradictions in our everyday reasoning about ourselves and our place in systems we simultaneously inhabit and attempt to describe, suggesting that our capacity to function might require us to ignore the logical impossibilities woven throughout our existence. Consider the ancient Cretan philosopher Epimenides, who made a simple statement that has echoed through 25 centuries of logic and philosophy: all Cretans are liars. The paradox emerges when we recognize that Epimenides himself was a Cretan, which means that if his statement is true, then he must be lying about Cretans being liars, which would make his statement false, which would then make it true again, trapping us in an infinite loop of logical contradiction that cannot be resolved through reason alone. This self-referential structure represents one of the oldest recorded versions of what would later become known as the liar's paradox, and it demonstrates how language can create statements that undermine their own truth conditions in ways that seem impossible to escape. The mechanism at work here involves what logicians call self-reference, where a statement makes a claim about the very category to which it belongs, creating a situation where determining its truth value becomes logically impossible because accepting either possibility generates its opposite. What makes this particularly relevant to our present moment is how we encounter Epimenides-like contradictions constantly in modern discourse. From social media algorithms that claim to reduce misinformation while simultaneously spreading it, to institutions that promise transparency while operating in opacity, to technology companies that assure us they prioritize privacy while collecting every detail of our existence. We have normalized living within these paradoxes rather than resolving them, accepting that certain systems contain internal contradictions that we simply cannot escape, and we continue to function within them as though they make perfect sense, treating logical impossibilities as ordinary features of contemporary life rather than as signs that something fundamental about the structure itself requires examination or reconstruction. Consider the author who has spent months or years researching and writing a substantial work, whether an academic treatise, a novel, or a comprehensive guide, and who then sits down to write the preface or introduction to that very book. In this preface, the author often expresses humility about the limitations of their work, acknowledges the gaps in their knowledge, admits to potential errors or oversights, and sometimes even apologizes for what the book fails to accomplish. The paradox emerges in this peculiar moment. The author is simultaneously asserting enough confidence in their work to publish it and declare it worthy of public attention, while simultaneously confessing to serious doubts about its reliability, completeness, or accuracy. If the author truly believed those criticisms expressed in the preface, the rational response would be to delay publication, conduct more research, revise substantially, or abandon the project entirely. Yet authors almost universally perform this strange ritual of public self-deprecation even as they commit their work to permanence. This creates a logical impossibility where the author claims to hold two mutually exclusive beliefs at once: that the work is sufficiently reliable to share with the world, and that it contains significant flaws or limitations that readers should know about. The mechanism underlying this paradox involves the human need to appear both competent and humble simultaneously, to maintain intellectual humility while still asserting authority. Authors have learned that audiences distrust those who claim perfection, so the preface becomes a performance space where vulnerability signals trustworthiness, even when that vulnerability contradicts the implicit claim that the book deserves to exist. What is remarkable is how completely normalized this contradiction has become, how neither authors nor readers find it strange that every book essentially begins by undermining its own credibility, and how we have collectively agreed to treat these confessions as mere social ritual rather than as genuine expressions of doubt that should prevent publication. Imagine a committee of 3 people voting on 3 candidates, Alice, Bob, and Carol. The first voter prefers Alice over Bob and Bob over Carol. The second voter prefers Bob over Carol and Carol over Alice. The third voter prefers Carol over Alice and Alice over Bob. When you tally the results by pairwise comparisons, something extraordinary emerges. A majority prefers Alice over Bob, a majority prefers Bob over Carol, and yet a majority also prefers Carol over Alice. You have arrived at a complete logical cycle with no clear winner, despite every individual voter holding perfectly rational and transitive preferences. This is the Condorcet Paradox, discovered by the 18th century mathematician and philosopher Marie-Jeanne Nicolas de Caratat, Marquis de Condorcet, and it reveals a fundamental fissure in how democratic aggregation operates at scale. The paradox demonstrates that rational individuals, when their preferences are combined through majority voting, can produce collectively irrational outcomes where no option emerges as superior to all others. This phenomenon becomes even more pronounced as voting populations grow larger and preference distributions become more diverse, making it not merely a theoretical curiosity, but a practical problem embedded in the very machinery of democratic decision-making. The psychological mechanism underlying this paradox lies in the assumption that collective preferences should behave like individual preferences, that groups should somehow develop singular, transitive preference orderings despite being composed of members with divergent values. Yet aggregation rules themselves possess mathematical properties that resist such clean transitivity, meaning the structure of voting systems can mathematically guarantee cycles regardless of how rational the individual voters might be. Consider the fundamental challenge that emerges whenever a group of people must make a collective decision by aggregating their individual preferences into a single outcome that supposedly represents the will of all parties involved, a problem that haunts democracies, committees, juries, and any institution claiming to honor both individual choice and collective unity. Kenneth Arrow's impossibility theorem, formulated in the 1950s, demonstrates that no voting system or preference aggregation method can simultaneously satisfy 4 seemingly reasonable criteria. Unrestricted domain allowing any configuration of individual preferences, non-dictatorship ensuring no single person controls the outcome, Pareto efficiency preventing outcomes where everyone prefers an alternative that isn't chosen, and independence of irrelevant alternatives, meaning the choice between 2 options depends only on how individuals rank those 2 options relative to each other. The logic is rigorous and mathematically inescapable, yet societies continue to pretend that their voting mechanisms represent genuine collective will, operating as though these contradictions do not exist or can be somehow circumvented through procedural cleverness. We watch this paradox unfold constantly in legislative bodies where the order of voting affects outcomes, in ranked choice elections where removing a candidate can change who wins, in committee meetings where the same group produces different results depending on how votes are tallied. Yet we treat these distortions as minor technical problems rather than fundamental evidence that collective preference aggregation is logically impossible. Imagine that engineers develop a revolutionary engine that consumes half the fuel it once did, cutting energy costs dramatically for every factory, vehicle, and home that adopts it. One would naturally assume that total fuel consumption would plummet, environmental impact would decrease, and resources would be conserved for future generations. Yet in the real world, something counterintuitive occurs. Total energy consumption actually increases. This phenomenon, first documented by economist William Stanley Jevons in the 19th century when studying coal consumption during the Industrial Revolution, reveals a fundamental flaw in how we approach efficiency. When technology makes something more efficient and therefore cheaper, demand for that resource paradoxically rises, often overwhelming any savings the efficiency created. Consider the modern smartphone. As processors became more efficient, they consumed less power per operation, yet we responded by using our phones constantly, enabling high-resolution video streaming, running multiple applications simultaneously, and keeping devices charged daily rather than weekly. The total energy consumption of global smartphone infrastructure skyrocketed despite tremendous efficiency gains. This same pattern repeats across heating systems, lighting, transportation, and computing. When air conditioning became more efficient, people set thermostats lower and cooled larger spaces. When cars became more fuel efficient, people drove longer distances and purchased larger vehicles. The psychological mechanism underlying this paradox operates through a combination of factors. Efficiency creates affordability, affordability creates accessibility, accessibility creates new use cases, and new use cases consume the savings. We do not consciously choose to waste the efficiency gain. Rather, we respond rationally to economic incentives by finding new ways to utilize a cheaper service. Imagine a family sitting together on a sweltering hot day in Texas, each member internally dreading the prospect of taking a long drive to Abilene, a town they have no genuine desire to visit. Yet somehow, through a series of careful observations and tentative suggestions, the entire family agrees to make the trip, each person believing that the others want to go, each person suppressing their own preferences to avoid being the one who disappoints the group. They drive to Abilene in uncomfortable silence, suffer through the experience, and return home exhausted and frustrated. When finally someone asks if anyone actually wanted to go, they discover with astonishment that not a single person wanted to make the journey at all. This is the Abilene Paradox, a phenomenon where groups collectively decide to do something that none of its individual members actually want to do. The mechanism underlying this paradox stems from a fundamental human fear of being perceived as selfish, obstructive, or unwilling to cooperate with the group consensus. Each member assumes that silence indicates agreement and that speaking up would mark them as the dissenting voice, the difficult personality, the one who ruins things for everyone else. This creates a false consensus where everyone believes everyone else wants something, and therefore feels obligated to conform to what they believe is the group's genuine desire. The paradox persists because we have normalized the suppression of individual preferences in favor of perceived collective harmony, even when that harmony is entirely illusory and built upon shared misunderstandings rather than actual agreement. We rarely pause to verify whether the group truly wants what it claims to want, and by the time we do, we are already committed to the course of action, making it psychologically easier to simply proceed rather than admit the entire endeavor was based on a cascade of false assumptions. Consider the experience of browsing a dating application where you encounter an endless stream of potential matches, each presented with a photograph, a brief biography, and a list of attractive qualities. You might notice that the most physically attractive people on the platform tend to have less impressive careers or personalities, while those with excellent jobs and interesting hobbies seem less conventionally beautiful. This observation leads you to conclude that attractiveness and success are somehow inversely correlated, that there exists a genuine negative relationship between these desirable traits. Yet when you step away from the application and examine the world around you, you see countless examples of people who possess both beauty and achievement simultaneously, suggesting that no such relationship actually exists outside this curated environment. This is Bergson's paradox, a statistical phenomenon discovered by Joseph Bergson in 1946, wherein a negative correlation appears to exist between two variables that are actually independent or even positively correlated in the broader population. The mechanism underlying this paradox emerges from the process of selection itself. Dating applications use complex algorithms to select which matches appear before you, and these algorithms prioritize showing you people who meet a minimum threshold of overall desirability. When such selection is applied to two independent variables, it creates a spurious negative correlation among those selected individuals. If someone is exceptionally attractive but has a mediocre career, they still clear the threshold because of their appearance. If someone has an outstanding career but is only moderately attractive, they still qualify because of their professional success. However, someone who is both unattractive and unsuccessful rarely appears in your feed at all because they fail to meet the algorithm's combined threshold. This filtering mechanism mathematically guarantees that among the selected subset, the two traits will appear inversely related even though they possess no causal connection in the general population. Consider the peculiar institution of the surprise examination, a pedagogical tool that has persisted in educational systems across the globe for generations, despite functioning in direct opposition to its own stated purpose of assessment. A teacher announces that there will be a surprise quiz or exam on unspecified material within an unspecified time frame, creating an impossible logical paradox that somehow remains normalized within our collective educational experience. The moment the teacher declares the exam to be a surprise, it ceases to be a surprise in any meaningful sense. Yet students are expected to maintain a state of perpetual anxiety and readiness as though the information had not been disclosed. This creates a psychological mechanism wherein the student's mind enters a state of generalized stress rather than focused preparation, and the examination then measures not comprehension, but rather the degree to which the student can perform under artificial pressure and uncertainty. The institution persists because it operates under the assumption that constant vigilance and anxiety are conducive to learning, when in fact neuroscience demonstrates that the human brain consolidates information most effectively during periods of calm, focused study, and adequate rest. Yet year after year, decade after decade, teachers continue to employ this contradictory method, students continue to experience the unnecessary stress it generates, and administrators continue to permit it, all while everyone involved tacitly acknowledges its illogical nature. We have normalized a system where the announcement of a surprise literally removes the possibility of surprise, where the stated goal of assessment is contradicted by the method of evaluation, and where the psychological harm is considered an acceptable byproduct of educational rigor. The surprise exam persists not because evidence supports it, but because it always has, suggesting we are operating within parameters we have inherited without question or revision. If you examine a sufficiently large data set of naturally occurring numbers, whether they be the populations of cities, the lengths of rivers, the stock prices of companies, or the death tolls recorded in historical documents, you will notice an extraordinary pattern that defies intuition. The digit 1 appears as the first digit far more frequently than any other numeral, showing up in roughly 30% of all cases, while the digit 9 appears as the first digit in less than 5% of all cases. This mathematical phenomenon, known as Benford's law, describes a logarithmic distribution of leading digits that appears across countless independent datasets in the natural world, a pattern so consistent and so pervasive that it seems almost impossible to explain through ordinary coincidence. When you would expect each digit from 1 through 9 to appear with roughly equal frequency as a leading digit, approximately 11% each, the universe instead produces a perfectly predictable skew toward lower numbers, a bias so precise that mathematicians have used it to detect fraud in financial records, tax documents, and election results, because when humans fabricate data, they unconsciously distribute digits more evenly than nature does. The mechanism underlying this phenomenon stems from the logarithmic nature of scale itself. As quantities grow exponentially in the real world, they spend more time in ranges beginning with 1 and 2 than in ranges beginning with 8 and 9, meaning that a naturally growing quantity spends roughly 9 times as long in the billions as it does crossing from 9 billion to 10 billion. Consider the peculiar situation wherein a physicist attempts to travel backward through time to prevent their own birth. Yet the very act of attempting such a journey creates the circumstances that make it necessary in the first place, establishing a causal loop that seems logically impossible, yet self-perpetuating through its own contradiction. Joseph Polchinski proposed this thought experiment as an extension of the grandfather paradox, but with a crucial twist that reveals something far more unsettling about the nature of causality itself. The paradox suggests that if you travel back in time to prevent your birth by killing your mother before she conceives you, the moment you succeed in this act, the reason for your time travel disappears entirely, which means you would never have been motivated to travel back in time in the first place, yet you are clearly present and performing the action. This creates not merely a logical contradiction, but an ontological impossibility, a state where an event must simultaneously occur and not occur for the causal chain to remain consistent. What makes this paradox particularly relevant to our potential simulation hypothesis is how it demonstrates that our universe, or any universe operating under similar physical laws, may be fundamentally constrained by logical rules that prevent genuine paradoxes from ever manifesting, suggesting that either time travel cannot work as we imagine, or that some invisible mechanism actively prevents contradictions from arising. We live within a system where such paradoxes remain eternally theoretical, never actualizing, never breaking the underlying consistency of reality itself, much as a well-designed simulation would need safeguards against logical glitches that would crash the entire system. The persistence of these paradoxes in our minds, despite their logical impossibility in practice, suggests we inhabit a realm where certain fundamental rules are non-negotiable, enforced at the deepest levels, perhaps by the very architecture of existence itself. Consider a scenario in which you glance at a clock on the wall and note the time is 3 o'clock in the afternoon, and based on this observation you form the belief that it is 3 o'clock. You feel confident in this belief because you have direct perceptual evidence. However, unknown to you, the clock is broken and stopped at 3 o'clock many hours ago, and by pure coincidence, it actually is 3 o'clock when you look at it. In this moment, you possess a belief that is true, and you arrived at that belief through what appears to be justified reasoning, yet something feels deeply wrong with calling this justified true belief knowledge. This is the essence of the Gettier Problem, a philosophical paradox that fundamentally challenges our understanding of what knowledge actually is. For centuries, philosophers accepted that knowledge could be simply defined as justified true belief. If you believe something, that belief is true, and you have adequate justification for holding that belief, then you have knowledge. This definition seemed airtight until philosopher Edmund Gettier published a brief paper in 1963 demonstrating that these three conditions were not sufficient. His counterexamples revealed that you could satisfy all three conditions simultaneously, yet still lack what we would intuitively call knowledge. What makes this paradox so deeply unsettling is that it exposes a gap between how we think knowledge functions and how it actually functions in edge cases that violate our intuitions. Our cognitive systems evolved to assume a relatively stable relationship between belief, justification, and truth, where these elements align through normal causal pathways. When we see the broken clock, our minds immediately sense something amiss, because the justification is accidentally aligned with the truth through no legitimate connection. The simulation hypothesis gains curious support from this problem because it suggests that our definitions of fundamental concepts like knowledge may be provisional frameworks we have constructed rather than discovered truths about reality. In the quantum realm, particles exist in a state of superposition, where they simultaneously occupy multiple states until observed or measured, a phenomenon that has been experimentally verified countless times and remains one of the most robust findings in modern physics. Yet the moment we attempt to measure these particles, the very act of observation causes what scientists call quantum decoherence, wherein the superposition collapses into a single, definite state, transforming the ghostly probability clouds of quantum mechanics into the concrete reality we perceive. This process happens instantaneously and completely, as if the universe were running a cleanup routine the moment we look at it, erasing all evidence of the particle's previous existence in multiple states simultaneously. The psychological mechanism at work here involves a profound cognitive dissonance that we have learned to simply accept without deeper scrutiny. The notion that reality itself behaves differently when unobserved than when observed, that consciousness or measurement fundamentally alters the fabric of existence at its most basic level, presents a logical paradox so severe that it should shake the foundations of our understanding. Yet we have normalized it into academic textbooks and university curricula as though it were merely another quirk of nature, rather than a suggestion that observation literally creates reality. What makes this particularly suspicious from the perspective of a simulated reality is that decoherence functions precisely like a computational system that only renders detail when necessary, that conserves processing power by maintaining low-resolution probability states until something demands specificity, collapsing the wave function only when the measurement function is called. Much as a rendering engine in a video game only generates visual detail in the player's field of view while leaving everything else in a state of unresolved possibility. Consider the profound cosmic coincidence that our universe appears to be geometrically flat, a condition so precisely calibrated that physicists have spent decades trying to understand why the curvature of spacetime sits almost exactly at zero when it could have been anything else. The universe's geometry was determined in the first fractions of a second after the Big Bang, and the conditions required for it to be this flat rather than positively or negatively curved are so extraordinarily specific that the margin of error amounts to less than 1 part in a trillion, a number so incomprehensibly small that even describing it strains our linguistic capacity. Yet here we are, observing a universe whose large-scale structure conforms almost perfectly to Euclidean geometry, allowing us to build our physics and mathematics upon flat space assumptions that work with uncanny precision. The mechanism behind this observation has traditionally been explained through cosmic inflation theory, which suggests that in the earliest moments of existence, space expanded so rapidly that any initial curvature was flattened out, much as the surface of a balloon appears flat when magnified infinitely. However, this explanation merely displaces the mystery rather than resolving it, because inflation itself requires an equally improbable set of initial conditions to function, and we find ourselves caught in a recursive chain of unlikely prerequisites that each demand their own miraculous fine-tuning. What becomes philosophically unsettling is how this flatness problem persists in our consciousness as a genuine puzzle, rather than prompting more fundamental questions about whether our observation of flatness itself might be constrained by the limitations of our existence within the system we are trying to measure. Consider the fundamental observation that our universe appears to be homogeneous and isotropic when observed on the largest scales. Yet this uniformity presents a profound puzzle that physicists have grappled with for decades. The horizon problem emerges from a simple but devastating question. How could the distant regions of our universe, regions so far apart that light itself has never had time to travel between them since the Big Bang, nevertheless maintain nearly identical temperatures and densities? When we look at radiation from opposite sides of the observable universe, we find them to be extraordinarily uniform, differing by only 1 part in 100,000, yet according to our standard cosmological models, these regions should be completely causally disconnected, meaning they should have had no opportunity whatsoever to communicate or equilibrate with one another. This uniformity should not exist, and yet it does with almost eerie precision. The mechanism behind our acceptance of this paradox is subtle and deeply embedded in how modern physics operates. When faced with observational contradictions, the scientific community tends not to abandon the framework itself, but rather to introduce additional mechanisms, invisible scaffolding added to support the existing structure. And in this case, that mechanism became cosmic inflation, a theoretical period of exponential expansion that supposedly smoothed out the universe before everything we observe today. Yet we have never directly observed inflation, never captured it occurring anywhere in the universe, never found definitive independent evidence for its necessity beyond its ability to solve the horizon problem it was invented to address. What is remarkable is how thoroughly this solution has been normalized, how it has become the default assumption taught in classrooms and assumed in research, despite being fundamentally unfalsifiable and resting on the inflation theory itself, requiring more exotic assumptions to make it work properly. In physics, one of the most perplexing inconsistencies between our understanding of the universe emerges from what researchers call the hierarchy problem, a fundamental mismatch in the scales at which different forces operate that seems almost deliberately engineered into the fabric of reality itself. The problem arises when physicists attempt to reconcile two of the most important forces in nature. Gravity, which operates at the massive scales we observe in our everyday experience and across the cosmos, and the electroweak force, which governs the behavior of subatomic particles at scales billions of times smaller. And yet gravity is inexplicably weaker than all the other fundamental forces by a factor so astronomically large that it defies rational explanation, roughly 1 septillion times weaker than electromagnetism. A discrepancy so vast that it cannot be accounted for by any known physical principle. The mathematical framework that physicists use to describe these forces predicts that the strength of gravity should be comparable to the other forces. And yet reality presents us with this glaring contradiction where the universe has decided, for reasons that remain entirely obscured, to make gravity operate under completely different rules with a strength parameter that seems almost randomly chosen rather than derived from any deeper underlying principle. What makes this problem particularly striking is that it suggests either our understanding of physics is fundamentally incomplete, requiring entirely new dimensions or particles we have yet to discover, or that there exists some profound symmetry or mechanism in the universe that actively suppresses the strength of gravity to these seemingly absurd levels. As though someone deliberately fine-tuned a control dial to make gravity dramatically weaker than it should be according to all our theories and equations. Consider the fundamental problem that emerges when we attempt to measure the precise location and momentum of a subatomic particle simultaneously, a constraint known as the uncertainty principle, which suggests that the universe itself resists the kind of complete informational mapping that classical logic would demand. Yet here is where the paradox deepens. Our universe appears to contain far more objects and states than any finite system of measurement could ever fully categorize or distinguish, and yet somehow the mathematics of quantum mechanics works perfectly, suggesting that reality does not actually require complete information to function. The pigeonhole principle, a basic mathematical truth, states that if you have more pigeons than pigeonholes, at least one hole must contain multiple pigeons, a simple statement of logical necessity. But quantum particles do not behave this way. They seem to occupy superpositions that transcend the binary logic of in this hole or that hole, instead existing in probabilistic clouds that become definite only upon observation. This creates a strange inversion. The universe contains an apparently infinite number of possible states and positions, yet a finite system of measurement, yet nothing breaks. The classical pigeonhole principle demands categorical certainty, yet quantum reality operates on ambiguity and potentiality, demonstrating that existence itself seems designed to sidestep the rigid constraints that logic insists must apply. We have normalized this by accepting probability distributions and wave function mathematics as simply how nature works, without fully confronting the radical implication that reality may not be bound by the same rules of information and categorization that govern closed systems. The universe tolerates infinite multiplicity within finite constraints because the very distinction between things only emerges through measurement, meaning that before observation, the pigeons and pigeonholes exist in a state of unmeasured superposition where the principle itself becomes philosophically meaningless. Consider the peculiar situation in mathematics, where we prove the existence of infinite sets and their properties using formal logic. Yet when we examine those very sets through the lens of countable models, structures that contain only countably many objects, we discover something unsettling. Even the infinite sets we've rigorously proven to exist can be represented within these countable frameworks, suggesting that infinity itself might be relative to our perspective rather than absolute. This is Skolem's paradox, named after Norwegian logician Thoralf Skolem, and it emerges from the Lorwenheim-Skolem theorem, which demonstrates that if a mathematical statement is true in some infinite model, then it is also true in some countable model. The paradox reveals itself when we contemplate that we can construct a countable model of set theory in which the real numbers, which we've formally proven to be uncountable, nonetheless exist, which appears to contradict the very proof of their uncountability. The mechanism underlying this strange situation involves a subtle distinction between what is true within a model and what is true about a model from an external perspective. The countable model genuinely satisfies all the axioms and theorems of set theory, including the theorem stating that real numbers are uncountable. Yet from outside that model we can enumerate all the elements ourselves, revealing the apparent contradiction to be a phantom born from perspective confusion. We have normalized this paradox by recognizing that uncountability is not an intrinsic property, but rather a relational one, dependent on what objects and functions exist within a given mathematical universe. And yet this normalization masks something deeply disquieting. The idea that our most fundamental concepts about size, infinity, and mathematical truth may be fundamentally dependent on arbitrary frameworks we've constructed, that what we call absolute mathematical reality might be merely one perspective among many equally valid interpretations. raising the inevitable question of whether any mathematical truth exists independently of the models we create to contain it. Consider the peculiar phenomenon where mathematicians and philosophers have long grappled with a deceptively simple question: what makes a number interesting or unremarkable? The paradox emerges when we attempt to define the set of all uninteresting numbers, those digits and mathematical entities that possess no special properties, no unique characteristics, and no reason for distinction within the vast landscape of numerical reality. Yet the moment we identify a number as uninteresting, we have granted it a property that makes it interesting, for it becomes the smallest uninteresting number or the first uninteresting number of a particular type, immediately elevating it from obscurity into relevance. This logical contradiction has puzzled minds for generations, revealing a fundamental flaw in our ability to categorize and classify the building blocks of mathematics itself. The mechanism driving this paradox stems from our inherent human compulsion to find meaning and significance in all things, even when examining abstract mathematical concepts that should remain purely objective. We cannot help but assign value judgments to numbers, cannot resist the urge to distinguish between the notable and the mundane, even though the properties we use to make these distinctions are fundamentally subjective and observer-dependent. What appears uninteresting to one mathematician may possess profound significance to another, depending on context, field of study, and mathematical framework. The paradox persists because we have normalized the contradiction within our intellectual systems, accepting that mathematics contains inherent logical gaps, and accepting that some of our most fundamental categorization systems collapse under their own weight. Consider the ancient thought experiment that has persisted through centuries of philosophical discourse, a puzzle so deceptively simple that its implications have largely been ignored by modern thinkers who prefer more contemporary paradoxes. A crocodile emerges from the river and seizes a child, and the crocodile's mother makes an unusual bargain with the distraught father. If the father can correctly predict whether the crocodile will eat the child or return the child unharmed, the child will be freed. But if the father's prediction proves incorrect, the child will be consumed. The father, faced with this impossible choice, declares that the crocodile will eat the child. Now the crocodile finds itself trapped in a logical bind that cannot be resolved through any rational action, because if it eats the child, the father's prediction would have been correct, meaning the child should have been returned. Yet if it returns the child, the father's prediction would have been false, meaning the child should have been eaten. In this paradox lies a fundamental truth about the nature of commitment and consequence in our reality. We are constantly making predictions about future events, while simultaneously being the agents who determine those futures, creating an endless recursion of self-referential causality that should theoretically paralyze decision-making. Yet humans navigate this paradox every single day without experiencing the cognitive breakdown that logic suggests should occur. We make promises knowing we might break them. We plan futures while acknowledging our own unpredictability. We act as though our choices are predetermined while simultaneously believing our choices determine our fate. The crocodile paradox reveals that consciousness itself may be the simulator's solution to an unsolvable equation, a way of forcing paradoxical situations to resolve through the simple expedient of allowing us to ignore their impossibility. Imagine a farmer who possesses 100 kilograms of potatoes, and these potatoes are freshly harvested from the earth, still wet with moisture, composed of 99% water and only 1% solid matter by weight. The farmer stores them in a warehouse where the environmental conditions shift gradually over time, and through the natural process of evaporation and dehydration, the potatoes lose moisture until they reach what we might call equilibrium with their surroundings. Eventually, when weeks have passed, these same potatoes now contain only 98% water instead of 99%, meaning the water content has decreased by 1 percentage point. Here emerges the profound logical trap. If the water content represented 99 of the 100 kilograms, that would be 99 kilograms of water. But when the water percentage drops to 98%, the entire mass of the potatoes has not decreased by merely 1 kilogram as intuition might suggest. Instead, the reduction in total weight is dramatically counterintuitive. The 1 kilogram of solid matter remains unchanged, but because this solid matter now represents 2% instead of 1% of the total mass must have dropped to 50 kilograms, meaning the farmer has mysteriously lost half of his potatoes through this seemingly minor change in water content. Our minds resist this conclusion because we operate with an embedded assumption that small percentage changes correspond to proportionally small absolute changes, yet percentage shifts compound and restructure the whole in ways that defy our everyday experience. We have built economic and agricultural systems atop this foundation of intuitive misunderstanding, never quite reconciling the mathematics with our expectations, creating a persistent gap between what the numbers tell us and what we believe should logically occur when something loses a single percentage point of moisture. Consider a musical phenomenon that defies the basic architecture of human perception itself. The Tritone Paradox, discovered by psychologist Diana Deutsch in the late 1970s, which presents two tones separated by the interval musicians call the tritone, an interval spanning 6 semitones that sits directly in the middle of an octave, creating what classical composers once called diabolus in musica, the devil's interval, because of its unsettling dissonance. When listeners hear this specific interval played in a particular way, something strange occurs within their auditory processing. They cannot reliably determine whether the second tone is higher or lower than the first, even though the physical reality of the sound waves is completely objective and measurable. Yet their brains somehow interpret this identical acoustic information in opposite ways depending on factors like their musical training, their native language, and possibly even their individual neurology. The tritone paradox emerges most clearly when the two tones are played in an ascending sequence, with each tone composed of multiple octaves stacked upon one another, creating an ambiguity in which octave the listener's attention focuses. And this ambiguous octave structure triggers what neuroscientists believe represents a fundamental constraint in how human brains process pitch information. What makes this phenomenon genuinely paradoxical is that two people listening to the exact same recording may experience completely opposite auditory perceptions, with one person consistently hearing the sequence as ascending while another hears it descending, and yet both are neurologically normal and possess typical hearing capabilities. The mechanism underlying this illusion appears to involve the way our brains extract pitch information from complex harmonic structures, and how our perceptual systems rely on contextual interpretation rather than pure signal processing, revealing that even something as seemingly fundamental as determining whether a sound goes up or down contains hidden assumptions and interpretative layers built into our sensory architecture. Consider the modern supermarket, where a typical consumer might encounter more than 300 varieties of breakfast cereal, or perhaps 50 different types of olive oil, each promising subtle variations in flavor, origin, or nutritional benefit. Yet when faced with such abundance, the average person experiences not liberation but paralysis, a profound sense of anxiety that often results in decision fatigue, dissatisfaction with whatever choice is ultimately made, and a nagging suspicion that somewhere among those infinite options exists a superior alternative that was regrettably overlooked. This phenomenon extends far beyond grocery aisles into every domain of contemporary life, from the paralyzing array of streaming services that leaves viewers scrolling for hours without watching anything, to the exhausting landscape of dating applications where the endless catalog of potential partners somehow makes genuine connection feel more distant, to the overwhelming proliferation of career paths and educational trajectories that leaves young people perpetually questioning whether their chosen direction was truly optimal or merely acceptable by default. The psychological mechanism underlying this paradox operates through a shift in how our minds evaluate satisfaction, where the availability of multiple options fundamentally alters the baseline expectation for what constitutes an acceptable outcome, transforming what should be a straightforward selection process into an exercise in regret minimization and counterfactual thinking, a constant mental inventory of roads not taken and choices not made. Consider the fundamental contradiction that emerges when a society commits itself entirely to the principle of unlimited tolerance. Those who advocate for absolute tolerance must inevitably encounter ideologies and movements that explicitly reject tolerance itself, and in confronting such intolerance, the tolerant society faces an impossible choice between betraying its core value or allowing that value to be systematically dismantled by those who exploit it. This is the paradox of tolerance in its purest form, first articulated by philosopher Karl Popper, yet it manifests constantly in our social and political structures without resolution. When a government or community establishes laws protecting free speech and expression as sacred principles, it simultaneously protects the speech of those who would abolish free speech if given power, creating a logical loop where tolerance must sometimes limit itself to survive at all. The mechanism at work here operates through a kind of weaponization of the tolerant system's own rules. Intolerant actors understand the constraints placed upon tolerant societies and deliberately use those constraints to advance positions designed to eventually restrict the very freedoms they currently exploit. We have normalized this paradox by pretending it does not exist, by suggesting that all speech deserves equal protection regardless of its intent, by treating the problem as merely philosophical rather than practical and urgent. Yet the paradox persists in our institutions, our platforms, and our courtrooms, where we continuously debate whether tolerance requires us to tolerate the intolerant, whether free speech includes the right to incite the elimination of others' rights, whether a democratic system can democratically vote itself into tyranny. Consider the philosophical proposition that the entire universe, in its current state with all of its apparent history, complexity, and memories, could have been created last Thursday, fully formed with every detail of the past already embedded within it. The world would function identically whether it truly began billions of years ago or emerged into existence 7 days ago with perfect retroactive consistency. Every fossil, every historical document, every photograph, every memory in every human mind would exist exactly as it does now, creating an experiential reality that is completely indistinguishable from genuine history. This thought experiment reveals a profound epistemological problem that haunts our understanding of reality itself. We possess no empirical method, no experiment, no observation that could definitively prove that last Thursdayism is false. Any evidence we might cite as proof of ancient history would itself be part of the created universe, implanted with the appearance of age and origin. The mechanism underlying this paradox operates in our tendency to assume that the past must exist independently somewhere outside our current moment, but consciousness and perception only ever occur in the present instant, meaning all knowledge of history arrives to us as information, interpretation, and memory rather than direct experience. We have normalized the acceptance of historical reality without confronting how impossibly difficult it actually is to verify that the world existed before this very moment. In a simulated reality, last Thursdayism becomes less a philosophical curiosity and more a demonstration of how arbitrary the distinction between actual creation and apparent history becomes when examining the nature of digital universes. A sufficiently advanced simulation would include complete backward consistency, making the simulation's true creation date fundamentally unknowable to inhabitants operating within it. Imagine that neuroscientists have perfected a machine that can simulate any experience you desire with perfect fidelity. You could experience climbing Mount Everest, winning an Olympic gold medal, falling in love, creating a masterpiece, or living an entire alternate life of wealth and achievement, all while your body remains in a lab chair. The machine is entirely safe, the simulations are indistinguishable from reality, and no one would ever know you were plugged in. Most people, when asked this philosophical question, immediately reject the machine. They say they would not choose to enter it, that they would prefer to live in actual reality, even if their real life contained less pleasure and fewer achievements than the simulated alternative. This widespread intuitive rejection reveals something profound about human nature that standard utilitarian philosophy cannot easily explain. If happiness and experience are all that matter, then the experience machine should be desirable, yet we recoil from it instinctively. This paradox suggests that we care deeply about something beyond mere experience. We care about whether our experiences are real, whether we are actually accomplishing things, whether our relationships are genuine connections with other conscious beings. We value truth and authenticity in a way that seems to transcend our desire for pleasure or contentment. Yet simultaneously, we live in an age where we increasingly construct curated versions of our lives for social media, where we consume entertainment that blurs the line between reality and fiction, where we spend hours in virtual worlds and digital simulations. The very thing we claim to reject philosophically, we are actively choosing to approach in our daily existence. We spend more time in simulated experiences than ever before in human history, consuming content designed to trigger emotional responses, substituting digital connection for physical presence, yet we rarely acknowledge this contradiction.